Tonight we will begin a long and gradual course in higher mathematics. We will move from the earliest ideas of number and measurement toward calculus, linear algebra, differential equations, probability, and several deeper structures that connect these subjects. The pace will be steady. Each idea will be introduced from its basic form and then developed carefully. You may follow every definition, or you may simply listen to the sequence of terms and explanations. You may fall asleep at any point. The subject will continue quietly, without requiring anything from you. Higher mathematics is not one isolated branch of knowledge. It is a collection of methods for describing quantity, structure, change, space, uncertainty, and logical dependence. Its modern language was formed over several thousand years. Some concepts appeared first in practical problems. Others emerged when mathematicians tried to make earlier methods more general, more precise, or more consistent. The course begins with numbers. A number is an abstract object used to express quantity, order, or magnitude. The earliest numerical systems were closely connected with counting physical objects. A group of 5 stones, 5 animals, and 5 marts could all be represented by the same abstract quantity. This separation of number from object was one of the central intellectual steps in the development of mathematics. Natural numbers are the counting numbers. Depending on convention, they begin with either 0 or 1. They continue without end. 1, 2, 3, 4, and so on. Natural numbers support addition and multiplication. If 2 natural numbers are added, the result is another natural number. If 2 natural numbers are multiplied, the result is also another natural number. This property is called closure. Natural numbers are not closed under subtraction. 3 minus 5 is not a natural number. To make subtraction generally possible, mathematics introduces the integers. The integers contain the positive natural numbers, 0, and the negative natural numbers. Negative numbers were not accepted immediately in every mathematical tradition. They were often treated with suspicion because they did not correspond easily to ordinary collections of physical objects. Over time, they became useful for representing debt, direction, temperature differences, and algebraic balance. The integers are closed under addition, subtraction, and multiplication. They are not closed under division. 3 divided by 2 is not an integer. To make division possible in a wider range of cases, mathematics introduces rational numbers. A rational number can be written as a ratio of 2 integers. The denominator must not be 0. Examples include 1/2, -7/3, and 5, because 5 can be written as 5 divided by 1. Every rational number has a decimal representation that either terminates or repeats. 1/2 becomes 0.5, 1/3 becomes 0.333, with the digit 3 repeating without end. The ancient Greeks discovered that some magnitudes cannot be expressed as ratios of integers. The best known example is the diagonal of a square whose side has length 1. By the Pythagorean theorem, the diagonal has length equal to the square root of 2. The square root of 2 is irrational. It cannot be written as a fraction of 2 integers. A classical proof assumes that the square root of 2 can be written as a fraction in lowest terms. Algebra then shows that both the numerator and denominator must be even. That contradicts the assumption that the fraction was in lowest terms. The conclusion is that no such fraction exists. Irrational numbers include the square root of 2, pi, and the number e. Rational and irrational numbers together form the real numbers. The real numbers can be represented by points on a continuous number line. Every point on the line corresponds to a real number. Every real number corresponds to a point on the line. The real number system is ordered. For any 2 distinct real numbers, one is greater than the other. It is also complete. Informally, completeness means that the real number line has no missing points. More precisely, every non-empty set of real numbers that is bounded above has a least upper bound. This property is called the least upper bound property. It is one of the foundations of mathematical analysis. There are also complex numbers. Complex numbers extend the real numbers by introducing a number called I. It is defined by the relation that I squared equals -1. A complex number has the form a plus b times I, where a and b are real numbers. The number a is called the real part. The number b is called the imaginary part. Complex numbers are useful because every non-constant polynomial with complex coefficients has at least one complex root. This statement is known as the fundamental theorem of algebra. The complex numbers form an algebraically closed field. The word field has a precise mathematical meaning. A field is a set equipped with addition, subtraction, multiplication, and division by non-zero elements, satisfying a collection of structural laws. The rational numbers, real numbers, and complex numbers are fields. The integers are not a field because division does not always produce an integer. Before moving further, it is useful to understand mathematical operations as rules. Addition combines quantities. Subtraction measures a difference or reverses addition. Multiplication represents repeated addition in elementary contexts, but its meaning becomes broader in advanced mathematics. Division reverses multiplication when the divisor is non-zero. Exponentiation represents repeated multiplication for positive integer powers. The expression a to the power of n means that a is multiplied by itself n times. The zero power is defined so that a to the power of 0 equals 1 for non-zero a. Negative powers represent reciprocals. The expression a to the power of -n equals 1 divided by a to the power of n. Fractional powers are related to roots. The expression a to the power of 1/2 represents the square root of a when the meaning is defined in the chosen number system. Exponents obey several laws. When powers with the same base are multiplied, their exponents are added. When one power is divided by another power with the same non-zero base, the exponents are subtracted. When a power is raised to another power, the exponents are multiplied. These rules are first learned as computational shortcuts. Later, they become structural properties that help define exponential and logarithmic functions. A logarithm reverses exponentiation. If b to the power of x equals y, then the logarithm of y to base b equals x. The base b must be positive and must not equal 1. Common logarithms use base 10. Natural logarithms use the base e. The number e is approximately 2.71828. It appears naturally in continuous growth, compound interest, probability, calculus, and differential equations. The natural logarithm is written as the logarithm with an implied base e. It has a special relationship with differentiation and integration. The derivative of the natural logarithm of x is 1 divided by x for positive x. The derivative of e to the power of x is e to the power of x. These facts will become clearer after the basic ideas of functions and limits are established. Arithmetic expressions are interpreted according to an agreed order of operations. Grouping symbols are evaluated first. Powers are evaluated first. Powers are evaluated before multiplication and division. Multiplication and division are handled before addition and subtraction. Operations of equal priority are usually processed from left to right. The purpose of this convention is not philosophical. It simply ensures that the same written expression has the same interpretation for every reader. Algebra begins when numbers are represented by symbols. A symbol such as x may represent an unknown number, a variable quantity, or a general element of a set. An equation states that two expressions are equal. Solving an equation means finding all values of the variables that make the equality true. The equation x plus 3 equals 7 has the solution x equals 4. The same operation must be applied to both sides to preserve equality. Subtracting 3 from both sides gives x equals 4. This balancing principle is the basis of elementary equation solving. An identity differs from an ordinary equation. An identity is true for every permitted value of its variables. The expression a plus b squared equals a squared plus 2ab plus b squared is an identity when the left side means the square of a plus b. An equation such as x squared equals 4 is true only for specific values. Its real solutions are 2 and -2. A polynomial is an expression formed from variables and coefficients using addition, subtraction, multiplication, and non-negative integer powers. A polynomial in one variable has the general form a sub n times x to the power of n plus lower degree terms. The highest exponent with a non-zero coefficient is the degree. A degree 1 polynomial is linear. A degree 2 polynomial is quadratic. A degree 3 polynomial is quadratic. A degree 3 polynomial is cubic. A degree 4 polynomial is quartic. Linear equations have the form ax plus b equals 0, with a not equal to 0. Their solution is x equals -b divided by a. Quadratic equations have the form ax squared plus bx plus c equals 0, with a not equal to 0. Their solutions are given by the quadratic formula. The solutions equal -b plus or minus the square root of b squared minus 4ac, all divided by 2a. The quantity b squared minus 4ac is called the discriminant. If the discriminant is positive, there are 2 distinct real roots. If it is 0, there is 1 repeated real root. If it is negative, there are 2 non-real complex roots. The quadratic formula can be derived by completing the square. Completing the square rewrites a quadratic expression as a squared linear expression plus a constant. This method is useful beyond equation solving. It also appears in analytic geometry, optimization, probability distributions, and integration. Polynomials can be added, subtracted, multiplied, and composed. They can also be divided. Polynomial division resembles ordinary long division. If a polynomial is divided by another non-zero polynomial, the result consists of a quotient and a remainder. The degree of the remainder is lower than the degree of the divisor. The factor theorem states that x minus r is a factor of a polynomial if and only if the polynomial equals 0 when x equals r. The remainder theorem states that the remainder after division by x minus r is the value of the polynomial at r. These theorems connect algebraic factorization with the roots of equations. A function is one of the central concepts of higher mathematics. A function assigns exactly one output to each permitted input. The set of permitted inputs is called the domain. The set in which outputs are taken is called the codomain. The set of outputs that actually occur is called the range or image. A function is often written as f of x. The symbol x denotes an input. The expression f of x denotes the corresponding output. For example, f of x equals x squared defines a function from the real numbers to the real numbers. Its domain may be all real numbers. Its range is the set of non-negative real numbers. The codomain and range are not always the same. For the squaring function, viewed as a function from the real numbers to the real numbers, negative real numbers belong to the codomain, but not to the range. Functions can be described by formulas, tables, graphs, algorithms, or verbal rules. A formula is convenient, but it is not the function itself. The function includes the rule together with its domain and codomain. The same formula can define different functions when the domains or codomains differ. A function is injective when different inputs always produce different outputs. It is also called one-to-one. A function is surjective when every element of the codomain is produced by at least one input. It is also called onto. A function is bijective when it is both injective and surjective. A bijective function has an inverse function. The inverse reverses the original assignment. If f sends x to y, then the inverse sends y back to x. The notation for the inverse is f to the power of -1. This notation does not usually mean the reciprocal 1 divided by f. It refers to functional inversion. Functions can be combined by composition. If f and g are functions, then f composed with g means that g is applied first and f is applied second. The resulting expression is f of g of x. Composition is generally not commutative. Applying f after g may produce a different result from applying g after f. Associativity does hold when the compositions are defined. This means that the grouping of 3 composed functions does not affect the final result. Several elementary families of functions recur throughout higher mathematics. Linear functions have the form f of x equals mx plus b. Their graphs are straight lines. The number m is the slope. It measures the change in the output per unit change in the input. The number b is a vertical intercept. It is the output when x equals 0. Quadratic functions have graphs called parabolas. The graph opens upward when the leading coefficient is positive. It opens downward when the leading coefficient is negative. The vertex is the point where the function reaches a minimum or maximum. Polynomial functions are continuous and smooth. Their graphs have no jumps, breaks, or sharp corners. Rational functions are ratios of polynomials. They may have points where they are undefined. These points occur where the denominator equals 0. Their graphs may have vertical, horizontal, or oblique asymptotes. An asymptote is a line that a graph approaches according to a specified limiting behavior. Power functions have the form x to the power of a constant. Exponential functions have the variable in the exponent. A typical exponential function has the form a to the power of x. When a is greater than 1, the function grows as x increases. When a lies between 0 and 1, the function decays as x increases. Logarithmic functions are inverses of exponential functions. They grow slowly. They convert multiplication into addition. The logarithm of a product equals the sum of the logarithms. The logarithm of a quotient equals the difference of the logarithms. The logarithm of a power equals the exponent multiplied by the logarithm of the base quantity. These properties made logarithms historically important for computation before electronic calculators. Multiplication could be replaced by addition through the use of logarithm tables. Trigonometric functions arise from geometry and periodic motion. The basic functions are sine, cosine, and tangent. For a right triangle, sine is the ratio of the opposite side to the hypotenuse. Cosine is the ratio of the opposite side to the hypotenuse. Tangent is the ratio of the opposite side to the adjacent side. These definitions apply directly to acute angles. The unit circle extends them to all real angles. The unit circle has radius 1 and is centered at the origin. An angle measured from the positive horizontal axis determines a point on the circle. The cosine of the angle is the horizontal coordinate. The sine is the vertical coordinate. Tangent is sine divided by cosine when cosine is not 0. Angles may be measured in degrees or radians. A full turn contains 360 degrees. A full turn contains 2 pi radians. 1 radian is the angle subtended at the center of a circle by an arc whose length equals the radius. Radians are the natural unit for calculus. When angles are measured in radians, the derivative of sine is cosine without any additional conversion factor. The derivative of cosine is negative sine. The sine and cosine functions are periodic. Their period is 2 pi. Tangent has period pi. Tangent has period pi. The identity sine squared of x plus cosine squared of x equals 1 follows from the equation of the unit circle. Other trigonometric identities can be derived from angle addition formulas. The sine of a plus b equals sine a times cosine b plus cosine a times cosine b plus cosine a. The cosine of a plus b equals cosine a times cosine b minus sine a times sine b. These identities support the analysis of oscillations, waves, rotations, and Fourier series. A graph represents the relation between input and output geometrically. For a function of one real variable, the horizontal axis usually represents the input. The vertical axis represents the output. Each point on the graph has coordinates x and f of x. Transformations of graphs correspond to changes in formulas. Adding a constant to a function shifts the graph vertically. Replacing x by x minus a shifts the graph horizontally by units to the right. Multiplying the output by a constant stretches or reflects the graph vertically. Multiplying the output by a constant compresses or reflects it horizontally. These transformations allow complicated graphs to be understood in terms of simpler ones. Analytic geometry combines algebra with geometry. Its development is associated especially with René Descartes and Pierre de Fermat in the 17th century. A point in the plane is represented by an ordered pair of numbers. The first coordinate gives horizontal position. The second gives vertical position. The distance between 2 points follows from the Pythagorean theorem. If the points are x1, y1, and x2, y2, the distance is the square root of the sum of two squared differences. A straight line can be represented by several equations. The slope-intercept form is y equals mx plus b. The point-slope form is y minus y1 equals m times x minus x1. The general linear form is a x plus b, y plus c equals 0. Two non-vertical lines are parallel when they have the same slope. They are perpendicular when the product of their slopes equals -1, provided both slopes are defined. A circle with center h, k, and radius r satisfies the equation x minus h squared plus y minus k squared equals r squared. Conic sections arise from intersecting a plane with a double cone. They include circles, ellipses, parabolas, and hyperbolas. They can also be defined by distance properties. An ellipse is the set of points for which the sum of the distances to two fixed points is constant. The fixed points are called foci. A hyperbola is a set of points for which the absolute difference of the distances to two fixed points is constant. A parabola is a set of points equidistant from a fixed point and a fixed line. The point is called the focus. The line is called the directrix. Conic sections appear in orbital mechanics, optics, engineering, and approximation theory. The next step is the concept of a sequence. A sequence is an ordered list of numbers. It can be viewed as a function whose domain is the natural numbers or positive integers. A sequence may be given by a formula. For example, a sub n equals 1 divided by n. The first terms are 1, 1/2, 1/3, 1/4, and so on. As n increases, these terms become arbitrarily close to 0. We say that the sequence converges to 0. The formal definition uses an arbitrary positive tolerance, a sequence. A sub n converges to L if, for every positive number epsilon, there exists a natural number n, such that the absolute value of a sub n minus L is less than epsilon, whenever n is greater than or equal to n. This definition expresses a precise idea. No matter how small a positive tolerance is chosen, all sufficiently late terms of the sequence lie within that tolerance of L. The number epsilon measures the permitted error. The number n marks how far into the sequence one must go. The order of these statements matters. The condition must work for every positive epsilon. The value of n may depend on epsilon. A convergent sequence has only one limit. Every convergent sequence is bounded. A bounded sequence need not converge. For example, the sequence whose terms alternate between 1 and -1 is bounded but does not approach a single number. A monotone increasing sequence never decreases. A monotone decreasing sequence never increases. A monotone sequence that is bounded converges. This result is called the monotone convergence theorem for sequences. It depends on the completeness of the real numbers. Some sequences diverge to positive infinity or negative infinity. This does not mean that infinity is an ordinary real number. It means that the terms eventually exceed every fixed real bound in the positive or negative direction. The sequence a sub n equals n grows without bound. The sequence negative n decreases without bound. Other sequences oscillate without approaching a limit. Convergence allows infinite processes to be treated with finite precision. An infinite series is formed by adding the terms of a sequence. The expression a 1 plus a 2 plus a 3 and so on is interpreted through partial sums. The nth partial sum is the sum of the first n terms. The infinite series converges if the sequence of partial sums converges. Its sum is the limit of the partial sums. A geometric series has terms of the form a, r squared, and so on. When the absolute value of r is less than 1, the series converges. Its sum is a divided by 1 minus r. When the absolute value of r is greater than or equal to 1, the geometric series generally diverges, except in trivial special cases such as a equal to 0. The harmonic series is 1 plus 1/2 plus 1/3 plus 1/4, and so on. Its terms approach 0. Nevertheless, the series diverges. This shows that terms approaching 0 is necessary for convergence, but not sufficient. The divergence can be demonstrated by grouping terms. After the first term, group the next one term, then the next two terms, then 4 terms, then 8 terms. Each group after the first has a sum of at least 1/2. Since infinitely many groups contribute at least 1/2, the partial sums grow without bound. The alternating harmonic series is 1 minus 1/2 plus 1/3 minus 1/4, and so on. It converges. Its sum is the natural logarithm of 2. The convergence is conditional. The series of absolute values is the ordinary harmonic series and diverges. A series is absolutely convergent when the series of the absolute values of its terms converges. Absolute convergence implies ordinary convergence. Conditional convergence is more delicate. Rearranging the terms of a conditionally convergent series can change its sum or cause divergence. This is the Riemann rearrangement theorem. Several tests help determine convergence. The comparison test compares a series with another series whose behavior is known. The ratio test examines the limiting size of consecutive term ratios. The root test examines nth roots of absolute values. The integral test compares a positive decreasing series with an improper integral. The alternating series test applies when terms decrease in magnitude towards 0 and signs alternate. Power series are infinite series involving powers of a variable. A power series centered at c has the form a0 plus a1 times x minus c plus a2 times x minus c squared, and so on. Every power series has a radius of convergence. Inside that radius, the series converges absolutely. Outside it, the series diverges. At the boundary, separate analysis is required. Power series allow functions to be represented by infinite polynomials. This leads to Taylor series. A Taylor series represents a sufficiently well-behaved function using its derivatives at one point. Centered at a, it begins with f of a. The next term is f prime of a times x minus a. The next is f double prime of a divided by 2 factorial times x minus a squared. The pattern continues with higher derivatives and factorial denominators. A Taylor series centered at 0 is called a Maclaurin series. The exponential function has the Maclaurin series 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, continuing indefinitely. Sine has the series x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial, continuing with alternating signs. Cosine has the series 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial, also with alternating signs. These series converge for every real and complex value of x. Not every infinitely differentiable function equals its Taylor series. Smoothness alone is not enough. A function may have derivatives of every order at a point while its Taylor series fails to represent the function away from that point. Functions that locally equal their convergent Taylor series are called analytic. The distinction between smooth and analytic functions becomes important in advanced analysis. If you're still listening closely, that is perfectly fine. The sequence of definitions can simply continue at an even and unhurried pace. We now arrive at limits of functions. The idea of a limit describes the behavior of a function near a point. The function does not necessarily need to be defined at the point. Suppose f of x approaches L as x approaches a. Informally, this means that f of x can be made arbitrarily close to L by taking x as sufficiently close to a, while x is not required to equal a. The formal definition uses epsilon and delta. We say that the limit of f of x as x approaches a equals L if, For every positive epsilon, there exists a positive delta such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is greater than 0 and less than delta. Epsilon controls the desired closeness of the output to L. Delta controls how close the input must be to a. The expression greater than 0 excludes the point x equals a. This is why the limiting value may exist even when the function is undefined. For example, consider the function x squared minus 1 divided by x minus 1. It is undefined at x equals 1. For every other x, it simplifies to x plus 1. As x approaches 1, the function approaches 2. The missing value at 1 does not change the limit. A two-sided limit exists only when the left-hand and right-hand limits both exist and are equal. The left-hand limit considers values smaller than a. The right-hand limit considers values larger than a. For the absolute value function divided by x, the left-hand limit at 0 is -1. The right-hand limit is +1. Therefore, the two-sided limit does not exist. Limits obey algebraic laws under appropriate conditions. The limit of the sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits when the denominator limit is not 0. Powers and roots can also pass through limits when their domains permit it. Some limits produce indeterminate forms. These include 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus infinity, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. An indeterminate form does not give the value of a limit. It indicates that further analysis is needed. Different expressions with the same apparent form can have different limits. The limit of x divided by x as x approaches 0 is 1 when x is non-zero. The limit of x squared divided by x as x approaches 0 is 0. Both initially appear as 0 divided by 0 through direct substitution, but their limiting behaviors differ. A function is continuous at a point a when three conditions hold. The value f of a is defined. The limit of f of x as x approaches a exists. The limit equals f of a. Continuity means that the function's local limiting behavior agrees with its actual value. A function is continuous on an interval when it is continuous at every point of that interval with appropriate one-sided conditions at endpoints. Polynomial functions are continuous everywhere. Rational functions are continuous wherever their denominators are non-zero. Exponential and trigonometric functions are continuous on their natural domains. Logarithmic functions are continuous for positive inputs. Continuity has important consequences. The intermediate value theorem states that a continuous function on a closed interval takes every value between its endpoint values. If a continuous function is negative at one endpoint and positive at the other, it must equal 0 somewhere between them. This theorem supports many root-finding methods. The extreme value theorem states that a continuous real-valued function on a closed and bounded interval reaches both a maximum and a minimum. The interval must be closed and bounded. Without these conditions, the conclusion may fail. For example, the function f of x equals x on the open interval from 0 to 1 has no maximum and no minimum within that interval. It approaches 0 and 1, but does not attain either endpoint value. Uniform continuity is stronger than ordinary continuity. Ordinary continuity allows the required delta to depend on both epsilon and the point under consideration. Uniform continuity requires one delta for each epsilon that works across the entire domain. Every continuous function on a closed and bounded interval is uniformly continuous. This is the Heine-Cantor theorem. The concept of compactness provides the deeper structure behind many such results. In Euclidean space, a set is compact if and only if it is closed and bounded. In general topological spaces, compactness is defined through open covers. Every open cover of a compact set has a finite subcover. This abstract definition will appear later when the language of topology is introduced. Limits also describe behavior at infinity. The statement that f of x approaches L as x approaches positive infinity means that f of x becomes arbitrarily close to L when x is sufficiently large. For example, 1 divided by x approaches 0 as x approaches positive infinity. A horizontal asymptote corresponds to this type of limiting behavior. The statement that f of x approaches positive infinity as x approaches a means that the function exceeds every positive bound when x is sufficiently close to a in the specified direction. A vertical asymptote often occurs in this situation. The function 1 divided by x squared approaches positive infinity as x approaches 0 from either side. The function 1 divided by x approaches negative infinity from the left and positive infinity from the right. Limits can be evaluated by algebraic simplification, comparison, known standard limits, series expansion, or L'Hopital's rule. One fundamental limit is the limit of sine x divided by x as x approaches 0. When x is measured in radians, the limit equals 1. This result can be established geometrically using inequalities in the unit circle. It supports the derivative formulas for sine and cosine. Another important limit defines the number e. The expression 1 plus 1 divided by n, all raised to the power n, approaches e as n approaches infinity. A related continuous form is the limit of 1 plus x raised to the power 1 divided by x as x approaches 0. This limit also equals e under appropriate one-sided interpretation where the expression is real. The derivative begins with the idea of instantaneous change. A secant line passes through 2 points on a graph. Its slope measures average change over an interval. For a function f, the average rate of change from x to x plus h is f of x plus h minus f of x divided by h. To obtain an instantaneous rate, the interval h is allowed to approach 0. The derivative of f at x is the limit of this difference quotient, provided the limit exists. The notation may be written as f prime of x. It may also be written as df divided by dx. The derivative is itself a function when it exists across a range of inputs. Geometrically, the derivative gives the slope of the tangent line. Physically, if position is a function of time, the derivative of position is velocity. The derivative of velocity is acceleration. Economically, a derivative may represent marginal cost or marginal revenue. Biologically, it may represent an instantaneous growth rate. The definition of derivative is local. It depends on the behavior of the function arbitrarily close to the point. A function may be continuous without being differentiable. The absolute value function is continuous at 0. It is not differentiable there because the left-hand slope is -1 and the right-hand slope is +1. A sharp corner prevents a unique tangent slope. Differentiability implies continuity. The converse is false. Some continuous functions fail to be differentiable at isolated points. More advanced examples are continuous everywhere and differentiable nowhere. The Weierstrass function is a famous example. It showed that continuous curves can be far more irregular than early intuition suggested. Basic derivative rules reduce the need to return to the limit definition every time. The derivative of a constant is 0. The derivative of x is 1. The derivative of x to the power n is n times x to the power n minus 1 for integer n, and more generally under suitable domain conditions for real or complex exponents, the derivative of a constant multiple is the constant times the derivative. The derivative of a sum is the sum of the derivatives. The product rule states that the derivative of f times g equals f prime times g plus f times g prime. The quotient rule states that the derivative of f divided by g equals g times f prime minus f times g prime divided by g squared when g is non-zero. The chain rule handles composition. The derivative of f of g of f of g of f of h of x multiplied by g of prime of x. The chain rule is one of the most important principles in calculus. It expresses how rates of change combine through nested dependence. If distance depends on time and temperature depends on distance, then temperature also depends on time. The total rate is obtained by multiplying the rate of temperature with respect to distance by the rate of distance with respect to time. The derivative of e to the power of x is e to the power of x. The derivative of a to the power of x is a to the power of x times the natural logarithm of a. The derivative of the natural logarithm of x is 1 divided by x for positive x. The derivative of the logarithm to base a is 1 divided by x times the natural logarithm of a. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of tangent x is secant squared x, where tangent is defined. Inverse trigonometric functions also have standard derivatives. The derivative of arcsine x is 1 divided by the square root of 1 minus x squared for input strictly between -1 and 1. The derivative of arctangent x is 1 divided by 1 plus x squared for every real x. These formulas follow from implicit differentiation and trigonometric identities. Implicit differentiation applies when a relation is not solved explicitly for one variable. For the circle x squared plus y squared equals r squared, differentiation with respect to x gives 2x plus 2y times dy divided by dx equals 0. Solving for the derivative gives dy divided by dx equals negative x divided by y. Where y is non-zero, this slope agrees with the geometric fact that the tangent to a circle is perpendicular to the radius. Higher derivatives are obtained by differentiating repeatedly. The second derivative measures the rate of change of the first derivative. For position, it represents acceleration. The third derivative of position is sometimes called jerk. In pure mathematics, higher derivatives describe increasingly detailed local behavior. The sign of the first derivative indicates whether a differentiable function is increasing or decreasing. When the derivative is positive on an interval, the function is increasing there. When it is negative, the function is decreasing. A critical point occurs where the derivative is 0 or undefined, while the function itself is defined. Critical points are candidates for local maxima, local minima, or other special behavior. The first derivative test examines the sign of the derivative on either side of a critical point. A change from positive to negative indicates a local maximum. A change from negative to positive indicates a local minimum. No sign change may indicate that neither occurs. The second derivative describes concavity. A positive second derivative usually indicates that the graph is concavely upward. A negative second derivative indicates concavity downward. A point of inflection is a point where concavity changes. The second derivative may equal 0 at an inflection point, but that condition alone is not sufficient. For example, x to the fourth has second derivative equal to 0 at 0, yet its concavity does not change there. The second derivative test classifies some critical points. If f prime of c equals 0 and f double prime of c is positive, then c is a local minimum. If f double prime of c is negative, then c is a local minimum. If f double prime of c is negative, then c is a local maximum. If the second derivative is 0, the test is inconclusive. Optimization uses derivatives to find maximum and minimum values. A typical problem begins by defining an objective function. Constraints are used to express the objective in terms of one or more independent variables. Critical points and boundary points are then examined. In a closed interval, the absolute maximum and minimum occur among the critical points and endpoints. Optimization appears in engineering design, economics, statistics, logistics, physics, and machine learning. The mean value theorem connects local and average change. Suppose a function is continuous on a closed interval and differentiable on the corresponding open interval. Then there exists at least one point inside the interval where the derivative equals the average rate of change across the entire interval. Geometrically, there is a tangent line parallel to the secant line joining the endpoints. Rolle's theorem is a special case. If the function has equal values at the two endpoints, then somewhere between them the derivative equals 0. The mean value theorem has many consequences. It helps prove that a function with zero derivative throughout an interval must be constant there. It supports error estimates, monotonicity arguments, and uniqueness results. Taylor's theorem gives a finite polynomial approximation together with a remainder term. The Taylor polynomial of degree n matches the function and its first n derivatives at the center point. The remainder measures the approximation error. One common form of the remainder is the Lagrange remainder. It involves the next derivative evaluated at some intermediate point. Taylor approximation explains why smooth functions often behave locally like polynomials. Near a point A, the linear approximation is f of a plus f prime of a times x minus a. This is also called the tangent line approximation. Including the quadratic term improves the approximation. Further terms may improve it again when the derivatives are controlled. Newton's method uses tangent lines to approximate roots. Starting with an initial estimate x sub n, the next estimate is x sub n minus f of x sub n divided by f prime of x sub n. Under suitable conditions, the sequence converges rapidly to a root. The method can fail when the initial estimate is poor, the derivative is too small, or the function behaves irregularly. Its convergence is often quadratic, near a simple root. This means that the number of correct digits may roughly double at each successful iteration. Related numerical methods include the bisection method and secant method. The bisection method is slower but highly reliable when a continuous function changes sign across an interval. It repeatedly halves the interval and keeps the half containing a sign change. The secant method replaces the derivative with a slope computed from two recent approximations. L'Hopital's rule evaluates certain indeterminate limits. If two differentiable functions both approach zero, or both grow without bound, then under suitable hypotheses the limit of their quotient may equal the limit of the quotient of their derivatives. The rule does not apply automatically to every quotient. Its conditions must be checked. It applies directly only to the form 0 divided by 0 and infinity divided by infinity. Other indeterminate forms can sometimes be transformed into these forms. The derivative also leads to differential notation. The differential dy is often written as f prime of x times dx. In elementary applications, dx may represent a small input change and dy the corresponding linearized output change. The actual change in y is delta y. For small delta x, delta y is approximately f prime of x times delta x. This approximation underlies sensitivity analysis and error propagation. Relative error compares an absolute error with the size of the measured quantity. If y depends on several variables, partial derivatives measure sensitivity to each variable separately. This leads naturally toward multivariable calculus. Before moving there, integration must be introduced. Integration began historically through problems of area, volume, accumulated quantity, and inverse differentiation. The definite integral can be defined using limits of sums. Suppose a function is defined on an interval from a to b. Divide the interval into many smaller subintervals. Choose a sample point in each subinterval. Multiply the function value at that point by the width of the subinterval. Add the product. The result is a Riemann sum. As the maximum subinterval width approaches 0, the sums may approach a limit. That limit is the Riemann integral of the function from a to b. The notation uses an elongated letter s. It represents a continuous sum. The expression integral from a to b of f of x dx represents accumulated signed area. Areas above the horizontal axis contribute positively. Areas below contribute negatively. The definite integral is a number. The indefinite integral represents a family of antiderivatives. An antiderivative of f is a function f whose derivative equals f. If f is one antiderivative, then f plus any constant is also an antiderivative. This is because the derivative of a constant is 0. The constant of integration records this family. The fundamental theorem of calculus connects differentiation and integration. Its first form states that accumulation defined by an integral produces an antiderivative. if is continuous, and f of x is the integral from a fixed point a to x of f of t dt, then f prime of x equals f of x. Its second form states that a definite integral can be evaluated using any antiderivative. The integral from a to b of f of x dx equals f of b minus f of a. This theorem unifies two problems that were historically studied separately. One problem concerns tangent slopes and instantaneous change. The other concerns areas and accumulated quantities. Differentiation and integration are inverse processes under appropriate conditions. Basic integration formulas were reverse derivative formulas. The integral of x to the power n is x to the power n plus 1 divided by n plus 1 plus a constant, provided n is not negative 1. The integral of 1 divided by x is a natural logarithm of the absolute value of x plus a constant on intervals that do not cross 0. The integral of e to the power x is e to the power x plus a constant. The integral of sine x is negative cosine x plus a constant. The integral of cosine x is sine x plus a constant. Integration is generally more difficult than differentiation. A derivative can usually be found through systematic rules. An elementary antiderivative may not exist even for a simple elementary function. For example, e to the power of negative x squared has no elementary antiderivative. Its definite integral is central to probability and leads to the error function. Integration by substitution reverses the chain rule. If an integrand contains a composite expression and its derivative, a new variable can simplify the integral. The substitution u equals g of x gives du equals g prime of x dx. The method transforms the integral into one involving u. After integration, the original variable is restored for indefinite integrals. For definite integrals, the limits can be changed to corresponding u values. Integration by parts reverses the product rule. The formula states that the integral of u dv equals uv minus the integral of v du. It is useful when an integrand is a product and differentiating one factor makes it simpler. Typical examples involve logarithmic, inverse trigonometric, polynomial, and exponential functions. Partial fraction decomposition applies to rational functions. A rational function with a denominator that factors can often be expressed as a sum of simpler fractions. These simpler terms can then be integrated using logarithms, arctangents, or elementary power rules. Trigonometric integrals use identities to transform powers and products of sine, cosine, tangent, and secant. Trigonometric substitution applies to expressions containing square roots of quadratic forms. A square root of a squared minus x squared suggests the substitution x equals a sine theta. A square root of a squared plus x squared suggests x equals a tangent theta. A square root of x squared minus a squared suggests x equals a secant theta. These substitutions reflect the Pythagorean trigonometric identities. Improper integrals extend definite integration to infinite intervals or unbounded integrands. An integral from a to infinity is defined as a limit of integrals from a to a finite endpoint, b as b approaches infinity. An integral with an infinite discontinuity is defined by approaching the problematic point through a limit. An improper integral converges if the corresponding limit exists and is finite. Otherwise, it diverges. The integral from 1 to infinity of 1 divided by x to the power p converges when p is greater than 1. It diverges when p is less than or equal to 1. This result parallels the convergence behavior of p-series. The integral from 0 to 1 of 1 divided by x to the power p converges when p is less than 1. It diverges when p is greater than or equal to 1. The location of the singularity changes the convergence condition. Definite integrals compute more than area. The volume of a solid with known cross-sectional area a of x is the integral of a of x over the relevant interval. A solid of revolution can be treated using disks, washers, or cylindrical shells. The arc length of a differentiable curve y equals f of x is the integral of the square root of 1 plus f prime of x squared. The surface area of a surface of revolution has a related formula involving arc length and distance from the axis. The average value of a function on an interval is 1 divided by the interval length times the definite integral of the function. If density varies along an object, integration determines total mass. Moments determine balance points and rotational properties. Probability densities are integrated to obtain probabilities. Rates are integrated to recover accumulated change. The net change theorem states that the integral of a rate of change equals the total change in the underlying quantity. If velocity is integrated over time, the result is displacement. If speed is integrated, the result is total distance traveled. The distinction matters when direction changes. Numerical integration estimates definite integrals when exact antiderivatives are unavailable or inconvenient. The midpoint rule approximates each subinterval using the function value at its midpoint. The trapezoidal rule approximates the graph using line segments. Simpson's rule uses quadratic approximations across pairs of subintervals. Error bounds depend on interval width and derivatives of the function. Reducing the step size usually improves accuracy. The rate of improvement differs between methods. The trapezoidal rule typically has global error proportional to the square of the step size. Simpson's rule typically has global error proportional to the fourth power of the step size under suitable smoothness assumptions. Calculus in one variable gives a foundation for understanding local change and accumulation. Many real systems depend on several variables at once. Temperature may depend on 3 spatial coordinates and time. Economic output may depend on labor, capital, technology, and policy parameters. A probability density may depend on many random variables. This leads to multivariable calculus. A function of 2 variables assigns an output to each ordered pair in its domain. It may be written as f of x and y. Its graph in 3-dimensional space is often a surface. Level curves are sets of points where the function has a constant value. A topographic map uses level curves to represent constant elevation. A function of 3 variables cannot be graphed as an ordinary surface in 3-dimensional space. Instead, it can be studied using level surfaces, slices, color maps, or symbolic analysis. Limits in several variables are more demanding than limits in one variable. For a limit to exist at a point, the function must approach the same value along every possible path to that point. Checking a few paths can prove that a limit does not exist if different paths produce different values. Checking finitely many paths cannot usually prove that a limit exists. A general argument is required. For example, the function xy divided by x squared plus y squared approaches different behavior depending on the chosen path near the origin. Along the x-axis, the function equals 0. Along the line I equals x, it equals 1/2 away from the origin. Therefore, the limit at the origin does not exist. Continuity in several variables is defined by agreement between the function value and the multivariable limit. Polynomial functions in several variables are continuous everywhere. Rational functions are continuous where their denominators are non-zero. Partial derivatives measure change with respect to one variable, while the others are held constant. For f of x and y, the partial derivative with respect to x treats y as constant. The partial derivative with respect to y treats x as constant. Partial derivatives are denoted by a rounded derivative symbol. They describe directional sensitivity along coordinate axes. The gradient collects all first partial derivatives into a vector. For a scalar function f of several variables, the gradient points in the direction of steepest local increase. Its magnitude gives the maximum directional rate of increase. The directional derivative in a unit direction, u equals the dot product of the gradient with u, provided the function is differentiable. Level surfaces are perpendicular to the gradient where the gradient is non-zero. This is because movement tangent to a level surface produces no first-order change in the function. The total differential gives a linear approximation. For a function of x and y, the differential df is approximately f sub x times dx plus f sub y times di. In more variables, one term appears for each independent variable. This formula supports uncertainty propagation and local sensitivity analysis. Differentiability in several variables is stronger than the existence of partial derivatives. A function may have all partial derivatives at a point without being continuous there. True differentiability requires a good linear approximation in every nearby direction. A sufficient condition is that the first partial derivatives exist and are continuous in a neighborhood. The tangent plane to a differentiable surface, z equals f of x and y at a point, is determined by the function value and its first partial derivatives. It is the multivariable analog of the tangent line. Higher partial derivatives describe second-order behavior. The Hessian matrix contains all second partial derivatives. For a function of two variables, it includes f sub x, f sub x, f sub xy, f sub yx, and f sub yx. Under suitable continuity conditions, the mixed partial derivatives are equal. This is often called Clairaut's theorem or Schwarz's theorem. The Hessian helps classify critical points. At a critical point, the gradient is zero. If the Hessian is positive definite, the point is a strict local minimum. If it is negative definite, the point is a strict local maximum. If it is negative, the point is a saddle point. If the Hessian is semi-definite or singular, the test may be inconclusive. For a function of two variables, the determinant of the Hessian provides a common classification test. If the determinant is positive and f sub x is positive, there is a local minimum. If the determinant is positive and f sub x is negative, there is a local maximum. If the determinant is negative, there is a saddle point. If it is zero, further analysis is needed. Constrained optimization asks for extrema under one or more equation. The method of Lagrange multipliers introduces auxiliary variables. Suppose f is optimized subject to g equals a constant. At a regular constrained extremum, the gradient of f is parallel to the gradient of g. Thus, the gradient of f is parallel to the gradient of g. Thus, the gradient of f equals lambda times the gradient of g. The scalar lambda is the Lagrange multiplier. It often has an interpretation as a sensitivity of the optimal value to a change in the constraint. With several constraints, one multiplier is introduced for each constraint. The method transforms a constrained problem into a system of equations. Multiple integrals extend accumulation to higher dimensions. A double integral accumulates a function over a region in the plane. A triple integral accumulates over a region in space. When the integrand is 1, a double integral gives area, and a triple integral gives volume. When the integrand is density, the integral gives mass. Iterated integration evaluates a multiple integral, one variable at a time. Fubini's theorem gives conditions under which the order of integration may be exchanged. For continuous functions on rectangular regions, the procedure is straightforward. For more general measurable functions, absolute integrability is an important, sufficient condition. Changing the order of integration can simplify a problem. A region difficult to describe with vertical slices may be simple. With horizontal slices, double integrals over non-rectangular regions require variable limits. The inner limits describe a slice of the region. The outer limits describe a slice as vary. A change of variables transforms coordinates. In one variable, substitution introduces a derivative factor. In several variables, the corresponding factor is the absolute value of a Jacobian determinant. The Jacobian measures local scaling of area or volume. Polar coordinates represent a point in the plane by radius and angle. The relations are x equals r cosine theta and y equals r sine theta. The area element becomes r dr d theta. The extra factor r is the Jacobian. Cylindrical coordinates add a vertical coordinate c. Spherical coordinates use a radius and two angles. Conventions for the angles vary. The volume element includes a factor involving the square of the radius and the sine of one angle. Coordinate changes exploit symmetry. Circular regions are often simpler in polar coordinates. Cylindrical regions are often simpler in cylindrical coordinates. Spheres and radial functions are often simpler in spherical coordinates. Vector fields assign a vector to each point in space. A velocity field assigns a velocity vector to each point in a moving fluid. An electric field assigns a force per unit charge vector. A gravitational field assigns acceleration. Vector calculus studies differentiation and integration of vector fields. The divergence of a vector field measures local net outward flow. A positive divergence indicates a source-like region. A negative divergence indicates a sink-like region. The curl measures local rotational tendency. In 3 dimensions, curl is another vector field. A field with zero curl on a suitable domain may be conservative. A conservative vector field is the gradient of a scalar potential. Line integrals accumulate quantities along curves. A scalar line integral may measure mass along a wire with variable density. A vector line integral may measure work done by a force field along a path. For a conservative field, the line integral depends only on the endpoints. The fundamental theorem for line integrals states that the integral of a gradient field along a curve equals the potential difference between the endpoints. The integral around every closed curve is zero in a conservative field under appropriate domain conditions. Green's theorem relates a line integral around a simple, closed plane curve to a double integral over the enclosed region. Stokes' theorem generalizes this relationship to surfaces in 3-dimensional space. It relates the circulation around a boundary curve to the flux of curl through the surface. The divergence theorem relates flux through a closed surface to the triple integral of divergence over the enclosed volume. These theorems share a common pattern. An integral of a derivative over a region is related to an integral of the original quantity over the boundary. The fundamental theorem of calculus is the one-dimensional form of this general principle. The language of differential forms later unifies these results into a single generalized Stokes theorem. We will now drift from calculus toward linear algebra. Linear algebra studies vectors, linear transformations, systems of linear equations, and the structures built from them. Its methods are central to geometry, physics, computer graphics, statistics, differential equations, optimization, and machine learning. A vector can be introduced as an ordered list of numbers. In 2 dimensions, a vector may have components x and y. In 3 dimensions, it may have components x, y, and z. Geometrically, a vector can represent displacement, velocity, force, or direction. Algebraically, it is an element of a vector space. Vectors can be added component by component. They can be multiplied by scalars. A scalar is an element of the underlying number field, usually the real or complex numbers. Vector addition is commutative and associative. There is a zero vector. Every vector has an additive inverse. Scalar multiplication distributes over vector addition. These and related properties define a vector space. A vector space need not consist of arrows. Polynomials form a vector space. Matrices of fixed size form a vector space. Continuous functions on an interval form a vector space. Solutions of a homogeneous linear differential equation form a vector space. The abstraction allows the same reasoning to apply across many different objects. A linear combination of vectors is an expression formed by multiplying each vector by a scalar and adding the results. The span of a collection of vectors is the set of all their linear combinations. The span is the smallest subspace containing those vectors. A set of vectors is linearly independent when no vector in the set can be formed as a linear combination of the others. Equivalently, the only linear combination equal to the zero vector is the one in which all coefficients are zero. If a non-trivial combination gives zero, the vectors are linearly dependent. A basis is a linearly independent set that spans the entire vector space. Every vector in the space has a unique coordinate representation relative to a basis. The number of vectors in a basis is the dimension of the space. All bases of a finite dimensional vector space have the same number of elements. The standard basis of real coordinate space of dimension n consists of vectors with one coordinate equal to 1 and all others equal to 0. Different bases provide different coordinate descriptions of the same abstract vector. A change of basis changes coordinates but not the underlying vector. This distinction is important in geometry and physics. A matrix is a rectangular array of numbers. An m by n matrix has m rows and n columns. Matrices represent linear transformations after bases are chosen. They also represent systems of linear equations, data tables, bilinear forms, graphs, and numerical operators. Matrices can be added when they have the same dimensions. They can be multiplied by scalars. Matrix multiplication is defined when the number of columns of the first matrix equals the number of rows of the second. The entry in row I and column j of the product is the dot product of row I from the first matrix with column j from the second. Matrix multiplication is associative. It is distributive over addition. It is generally not commutative. The product AB may differ from BA. One product may be defined while the other is not. The identity matrix acts like the number 1 under matrix multiplication. It has ones on the main diagonal and zeros elsewhere. A square matrix is invertible when there is just another matrix whose product with it in either order is the identity. The inverse is unique. Not every square matrix is invertible. An invertible matrix is invertible. An invertible matrix is also called non-singular. A non-invertible matrix is called singular. Systems of linear equations can be written in matrix form. The expression AX equals B represents a coefficient matrix A, an unknown vector X, and a constant vector B. Gaussian elimination solves such systems through elementary row operations. The allowed operations are swapping two rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another. These operations preserve the solution set. The goal is to transform the augmented matrix into row echelon form or reduced row echelon form. A pivot is a leading non-zero entry in a row. Pivot positions reveal the rank of the matrix. The rank is the dimension of the row space. It is also the dimension of the column space. These two dimensions are always equal. A system may have one solution, infinitely many solutions, or no solution. For a square system, a unique solution exists exactly when the coefficient matrix is invertible. For a general system, consistency depends on whether B belongs to the column space of A. Free variables produce families of solutions. The homogeneous system AX equals 0 is always consistent because the zero vector is a solution. Its set of solutions called the null space or kernel. The rank nullity theorem states that the dimension of the domain equals the rank plus the nullity. For an MBA-SMOM matrix viewed as a linear map from n-dimensional coordinate space, n equals the rank plus the dimension of the null space. A linear transformation preserves vector addition and scalar multiplication. If T is linear, then T of U plus V equals T of U plus T of U plus T of V. Also, T of CU equals C times T of U. These two properties can be combined into preservation of all linear combinations. Every matrix defines a linear transformation between coordinate spaces. Every linear transformation between finite dimensional vector spaces can be represented by a matrix after bases are selected. The kernel of a linear transformation contains all vectors mapped to 0. The image contains all possible outputs. The transformation is injective exactly when its kernel contains only the 0 vector. It is surjective exactly when its image equals the codomain. For finite dimensional spaces of equal dimension, injectivity, surjectivity, and invertibility are equivalent. The determinant is a scalar associated with a square matrix. For a 2x2 matrix with entries A, B, C, and D, the determinant is a D minus B, C. The determinant measures signed area scaling in 2 dimensions and signed volume scaling in higher dimensions. A determinant of 0 means that the transformation collapses dimension. The matrix is then singular. A non-zero determinant means that the matrix is invertible. Determinants multiply. The determinant of AB equals the determinant of AB equals the determinant of B. The determinant of the identity is 1. The determinant of an inverse is the reciprocal of the original determinant. Swapping two rows changes the sign of the determinant. Multiplying a row by a scalar multiplies the determinant by that scalar. Adding a multiple of one row to another leaves the determinant unchanged. Cramer's rule expresses the solution of a square invertible system using determinants. It is theoretically elegant, but usually inefficient for large numerical systems. Gaussian elimination is computationally preferable. The dot product gives a notion of angle and length. For real coordinate vectors, the dot product is the sum of products of corresponding components. The squared length of a vector is its dot product with itself. The length is the square root of that value. Two vectors are orthogonal when their dot product is 0. For non-zero vectors, the cosine of the angle between them equals their dot product divided by the product of their lengths. The Cauchy-Schwarz inequality states that the absolute value of a dot product is at most the product of the vector lengths. Equality holds exactly when the vectors are linearly dependent. The triangle inequality states that the length of a sum is at most the sum of the lengths. These inequalities are fundamental in geometry and analysis. An inner product generalizes the dot product. It assigns a scalar to a pair of vectors and satisfies linearity, symmetry or conjugate symmetry, and positive definiteness. In complex vector spaces, the inner product uses complex conjugation. A norm measures size. Every inner product induces a norm. Not every norm comes from an inner product. A metric measures distance. A norm induces a metric by taking the norm of the difference between two vectors. These layers of structure lead from linear algebra into functional analysis and topology. Orthogonal projection gives the closest point in a subspace under the Euclidean norm. If a vector is projected onto a line spanned by a non-zero vector u, the projection equals a dot product of the original vector with u, divided by the dot product of u with itself, multiplied by u. Projection decomposes a vector into a component inside the subspace and an orthogonal residual. Least squares approximation uses this idea. An overdetermined linear system may have no exact solution. The least squares solution minimizes the squared length of the residual ax minus b. The residual at the optimum is orthogonal to the column space of A. This leads to the normal equations A transpose times A times x equals A transpose times B. When the columns of A are linearly independent, A transpose A is invertible and the least squares solution is unique. In numerical work, directly solving the normal equations may reduce stability. QR decomposition is often preferred. The Gram-Schmidt process converts a linearly independent set into an orthogonal or orthonormal set spanning the same subspace. An orthonormal set consists of mutually orthogonal unit vectors. Coordinates relative to an orthonormal basis are easy to compute using inner products. Classical Gram-Schmidt can suffer from numerical loss of orthogonality. Modified Gram-Schmidt is more stable. Householder reflections provide another robust method for QR factorization. A matrix decomposition expresses a matrix as a product of structured matrices. Lu decomposition factors a matrix into lower and upper triangular matrices, sometimes with a permutation matrix. It supports efficient solution of several systems with the same coefficient matrix. QR decomposition factors a matrix into an orthogonal or unitary matrix and an upper triangular matrix. It is useful for least squares and eigenvalue algorithms. The singular value decomposition factors a matrix into a product U sigma V transpose, or U sigma V conjugate transpose in the complex case. The diagonal entries of sigma are non-negative singular values. The singular value decomposition exists for every real or complex matrix. It reveals rank, conditioning, geometric scaling, and low-dimensional structure. It is one of the most useful decompositions in applied mathematics. An eigenvector of the square matrix is a non-zero vector whose direction is preserved by the transformation. The matrix may stretch, shrink, or reverse the vector. If AV equals lambda V, then V is an eigenvector and lambda is the corresponding eigenvalue. Eigenvalues satisfy the characteristic equation. The determinant of A minus lambda I equals 0. The characteristic polynomial has degree equal to the matrix size. Over the complex numbers, It has as many roots as its degree when multiplicities are counted. The eigenspace associated with an eigenvalue is the null space of A minus lambda I. A matrix is diagonalizable if it has a basis of eigenvectors. In that basis, the matrix becomes diagonal. Powers of a diagonal matrix are easy to compute. This simplifies repeated transformations, recurrence relations, and systems of differential equations. Not every matrix is diagonalizable. A matrix with too few independent eigenvectors requires a more general form. The Jordan canonical form organizes a complex square matrix into Jordan blocks. It provides a theoretical classification of linear transformations. It is sensitive to numerical perturbations and is rarely computed directly in floating-point applications. For real symmetric matrices, the situation is especially simple. The spectral theorem states that every real symmetric matrix has real eigenvalues and an orthonormal basis of eigenvectors. It can be diagonalized by an orthogonal matrix. For complex remission matrices, the corresponding statement uses unitary matrices and real eigenvalues. Positive definite matrices are symmetric matrices whose quadratic form is positive for every non-zero vector. Their eigenvalues are positive. They appear in optimization, probability, numerical analysis, and geometry. A covariance matrix is positive semi-definite. A Hessian at a strict local minimum is often positive definite. The Cholesky decomposition factors a positive definite matrix into a lower triangular matrix times its transpose. It is efficient and numerically stable. If you are still with the lecture, there is no need to hold every term in active attention. The definitions can pass quietly, one after another. Linear algebra also explains systems that evolve in discrete steps. A recurrence relation defines each term using earlier terms. The Fibonacci sequence satisfies the relation that each term equals the sum of the previous two. It can be represented using a 2x2 matrix. Powers of that matrix generate later terms. Diagonalization leads to a closed formula involving the golden ratio. The golden ratio is 1 plus the square root of 5 divided by 2. Its conjugate is 1 minus the square root of 5 divided by 2. The exact Fibonacci formula is often called Binet's formula. Markov chains also use repeated matrix multiplication. A finite state Markov chain has a transition matrix. Its entries give probabilities of moving between states. A probability distribution evolves by multiplication with the transition matrix. A stationary distribution remains unchanged under the transition. Eigenvectors associated with eigenvalue 1 describe stationary behavior. Convergence to a unique stationary distribution requires additional conditions, such as irreducibility and aperiodicity in the finite state case. We now move toward differential equations. A differential equation relates an unknown function to one or more of its derivatives. Differential equations describe motion, growth, decay, diffusion, oscillation, electrical circuits, fluid flow, heat transfer, chemical reactions, and population dynamics. An ordinary differential equation involves derivatives with respect to one independent variable. A partial differential equation involves partial derivatives with respect to several variables. The order of a differential equation is the highest derivative that appears. A first-order equation involves the first derivative. A second-order equation may involve the second derivative. A linear differential equation depends linearly on the unknown function and its derivatives. Nonlinear equations include products, powers, or nonlinear functions of the unknown quantity or its derivatives. A solution is a function that satisfies the equation on a specified interval. A general solution contains arbitrary constants. An initial condition selects a particular solution by specifying values at one point. A boundary condition specifies values at two or more points or along a boundary. The simplest first-order equation is y prime equals a given function of x. Its solution is obtained by integration. If y prime equals f of x, then y equals an antiderivative of f plus a constant. A separable differential equation has the form y prime equals g of x times h of y. It can be rearranged so that terms involving y appear on one side and terms involving x on the other. One then integrates both sides. Care must be taken with equilibrium solutions that may be lost during division. An exponential growth equation has the form y prime equals ky. Its solutions are y equals c e to the power kx. When k is positive, the magnitude grows exponentially. When k is negative, it decays. Radioactive decay, idealized population growth, and continuous compound interest use this model. The half-life is the time required for a decaying quantity to reach half its value. For exponential decay, the half-life equals the natural logarithm of 2 divided by the absolute value of the decay constant. A more realistic population model is the logistic equation. It has the form y prime equals ry times 1 minus y divided by k. The constant r is an intrinsic growth rate. The constant k is a carrying capacity. When y is small relative to k, growth is approximately exponential. As y approaches k, growth slows. The equilibrium solutions are 0 and k. The positive equilibrium k is stable when r is positive. A first-order linear differential equation has the form y prime plus p of x times y equals q of x. It is solved using an integrating factor. The integrating factor is e raised to the integral of p of x. Multiplying the equation by this factor turns the left side into the derivative of a product. Integration then gives the solution. Exact differential equations arise from expressions of the form m of x and y dx plus n of x and y dy equals 0. The equation is exact when there exists a potential function whose partial derivatives are m and n. A common test checks whether the partial derivative of m with respect to y equals the partial derivative of n with respect to x on an appropriate domain. If the equation is not exact, an integrating factor may sometimes make it exact. Existence and uniqueness theorems state when an initial value problem has a solution and whether that solution is unique. For the equation y prime equals f of x and y, continuity of f near an initial point often guarantees local existence. A Lipschitz condition in y gives local uniqueness. The Picard-Lindelof theorem provides a standard result. Its proof uses successive approximation in a contraction mapping argument. The theorem does not say that every solution exists for all time. A solution may become unbounded in finite time. For example, y prime equals y squared with a positive initial value has a solution that blows up after a finite interval. Second-order linear equations have the general form a of x times y, double prime plus b of x times y double prime plus b of x times y equals g of x times y equals g of x. When g equals 0, the equation is homogeneous. The solutions of a homogeneous linear equation form a vector space. For a second-order equation, the solution space typically has dimension 2 on intervals where the leading coefficient is non-zero. A general homogeneous solution is a linear combination of two independent solutions. For constant coefficients, one assumes a solution of the form e to the power rx. Substitution produces a characteristic polynomial. For the equation, a y double prime plus by prime plus cy equals 0. The characteristic equation is a r squared plus br plus c equals 0. Two distinct real roots give two exponential solutions. A repeated real root gives an exponential and x times that exponential. Complex conjugate roots alpha plus or minus beta I give oscillatory solutions. The real form is e to the power alpha x times a linear combination of cosine beta x and sine beta x. A mass spring system without damping satisfies an equation of the form mx double prime plus kx equals 0. Its solutions are sinusoidal. The angular frequency is the square root of k divided by m. Adding damping gives mx double prime plus cx prime plus kx equals 0. The behavior depends on the discriminant of the characteristic equation. Strong damping produces overdamped motion without oscillation. Critical damping returns to equilibrium as rapidly as possible without oscillation. Weak damping produces oscillations with exponentially decreasing amplitude. An external force produces a non-homogeneous equation. Periodic forcing can produce resonance when the forcing frequency is near the system's natural frequency. In an ideal undamped model, exact resonance can lead to amplitude growing without bound. Physical systems include damping and nonlinear effects that alter this ideal behavior. A particular solution of a non-homogeneous equation can be found by methods such as undetermined coefficients or variation of parameters. Undetermined coefficients work for certain forcing terms, including polynomials, exponentials, sines, cosines, and their products. Variation of parameters is more general. The full solution equals a homogeneous solution plus one particular solution. Systems of first-order differential equations can be written in vector form. The linear system x prime equals ax has solutions controlled by the matrix ax has solutions controlled by the matrix A. When A is diagonalizable, eigenvalues and eigenvectors separate the system into independent modes. An eigenvalue with negative real part produces decay. A positive real part produces growth. A non-zero imaginary part produces oscillation. Stability depends on the spectrum. The matrix exponential e to the power at generalizes the ordinary exponential. It is defined by a power series. The solution of x prime equals ax with initial value x0 is e to the power at times x0. The matrix exponential satisfies many familiar exponential properties. But e to the power a plus b equals e to the power a times e to the power b only when a and b commute. Phase planes visualize two-dimensional autonomous systems. A state is represented by a point. A solution traces a trajectory. Equilibria occur where all derivatives vanish. Linearization uses the Jacobian matrix near an equilibrium. Eigenvalues of the Jacobian classify many local behaviors. A stable node has trajectories approaching along non-oscillatory directions. An unstable node has trajectories moving away. A saddle has both stable and unstable directions. A spiral involves rotation combined with growth or decay. A center has nearby closed curves in the ideal linear case. Nonlinear systems can display limit cycles, bifurcations, and chaos. A bifurcation occurs when a qualitative feature of the system changes as a parameter varies. A saddle node bifurcation creates or destroys equilibria. A transcritical bifurcation exchanges stability between equilibria. A pitchfork bifurcation often reflects symmetry. A hop bifurcation creates or destroys periodic behavior near an equilibrium. Chaos refers to deterministic behavior with sensitive dependence on initial conditions. The equations are fixed and contain no random input. Nevertheless, nearby initial states can separate exponentially. The Lorentz system is a classical example. It was derived as a simplified model of atmospheric convection. Its trajectories can approach a complicated set known as the Lorentz attractor. Chaos does not mean complete absence of structure. Chaotic systems may have invariant sets, statistical regularities, and geometric organization. Partial differential equations extend these ideas to fields distributed across space and time. The heat equation describes diffusion in one spatial dimension. It has the form U sub t equals alpha times U sub xx. The constant alpha is diffusivity. The equation smooths temperature differences over time. High-frequency spatial variations decay faster than low-frequency variations. The wave equation describes propagation. In one dimension, U sub tt equals c squared times U sub xx. The constant c is wave speed. Solutions can be written as combinations of waves traveling in opposite directions. This is D'Alembert's formula on an infinite line. The Laplace equation is the sum of second spatial partial derivatives equal to zero. Its solutions are called harmonic functions. They describe steady-state temperature, electrostatic potential in charge-free regions, and incompressible potential flow. The Poisson equation adds a source term. Boundary conditions strongly affect the solution of a partial differential equation. Dirichlet conditions specify the value of the function on the boundary. Newman conditions specify the normal derivative. Robin conditions specify a linear combination of value and normal derivative. Initial conditions specify the state at a starting time. A problem is well posed when a solution exists, is unique, and depends continuously on the given data. Hadamard emphasized these three requirements. Some equations are ill-posed in certain time directions. The backward heat equation is a standard example. Small errors in later temperature data can correspond to enormous differences in reconstructed earlier states. Separation of variables seeks solutions as products of functions, each depending on one coordinate. For the heat equation on a finite interval, one may assume u of x and t equals x of x times t of t. Substitution separates the equation into an equation for x and another for t. Boundary conditions produce an eigenvalue problem. The spatial solutions are often sines or cosines. The temporal factors decay exponentially. The full solution is an infinite series of separated modes. Fourier series represent periodic functions as sums of sines and cosines. For a function with period 2π, the series contains a constant term, cosine terms, and sine terms. The coefficients are computed by integrals using orthogonality. Under suitable conditions, the Fourier series converges to the function at points of continuity. At a jump discontinuity, it converges to the average of the left and right limits. Near jumps, partial sums exhibit overshoot known as the Gibbs phenomenon. The overshoot does not vanish in relative height, though it becomes confined to a narrower region. Fourier methods convert differentiation into multiplication by frequency. They are central to signal processing, acoustics, optics, quantum mechanics, and numerical analysis. The Fourier transform extends Fourier analysis to non-periodic functions on the real line. It decomposes a function into a continuous spectrum of frequencies. Different normalization conventions are used. The transform of a derivative is multiplication by a frequency factor. The transform of a convolution is the product of transforms. The transform of a product corresponds to convolution in frequency space, up to convention-dependent constants. The Gaussian function has a Gaussian Fourier transform. This self-similarity contributes to its importance in probability and physics. The Laplace transform converts a function of time into a function of a complex frequency variable. It is particularly useful for initial value problems. Derivatives transform into algebraic expressions involving initial data. Differential equations can then become algebraic equations. After solving in the transform domain, an inverse transform recovers the original function. The transform also handles discontinuous forcing and impulse inputs. The Dirac delta is not an ordinary function. It is a distribution or generalized function. It is concentrated at a point and has total integral 1 in a formal sense. It models an idealized impulse. Distributions extend differentiation to non-smooth objects. The derivative of a step function is a delta distribution. This framework makes many operations in physics and differential equations mathematically precise. We now turn toward probability. Probability provides a mathematical language for uncertainty. It does not require that events be fundamentally random. It can also represent incomplete information, variability, or repeated sampling. A probability space consists of a sample space, a collection of events, and a probability measure. The sample space contains all possible outcomes. The events are selected subsets of the sample space. The probability measure assigns each event a number between 0 and 1. The probability of the entire sample space is 1. For disjoint events, the probability of their union is the sum of their probabilities. These are the Kolmogorov axioms. An event with probability 0 is not always impossible in continuous models. A single exact value under a continuous distribution usually has probability 0. Yet some value must occur. Likewise, An event with probability 1 is not always logically certain outside finite or countable settings. Such events are described as almost sure. Conditional probability measures probability after information is given. The probability of A given B equals the probability of both A and B divided by the probability of B, provided B has positive probability. Two events are independent when the probability of their intersection equals the product of their probabilities. Equivalently, learning that one occurred does not change the probability of the other when the relevant conditional probabilities are defined. Independence is stronger than mutual exclusivity. Two mutually exclusive events with positive probability cannot be independent. If one occurs, the other cannot occur. Bayes' theorem reverses conditioning. The probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. The theorem combines prior probability with likelihood. The result is a posterior probability. In applications, the denominator can be expanded using the law of total probability. Bayesian inference applies this principle to statistical models. A random variable is a measurable function from the sample space to the real numbers or to another measurable space. Despite its name, a random variable is a function. It assigns a numerical value to each outcome. A discrete random variable takes values in a finite or countable set. A continuous random variable is often described by a probability density. A probability mass function gives the probability of each discrete value. A density does not give point probabilities directly. Probabilities are obtained by integrating the density over intervals or regions. A cumulative distribution function gives a probability that a random variable is less than or equal to a given value. Every random variable has a cumulative distribution function. It is non-decreasing and right-continuous. It approaches 0 toward negative infinity and 1 toward positive infinity. The expected value is a probability-weighted average. For a discrete random variable, it is the sum of each value times its probability. For a continuous variable with density, it is the integral of x times the density. The expected value need not be a possible outcome. It may also fail to exist when positive and negative contributions do not converge appropriately. Variance measures average squared deviation from the mean. It equals the expectation of the square minus the square of the expectation. Standard deviation is the square root of variance. Variance has squared units. Standard deviation has the same units as the original quantity. Covariance measures joint linear variation between two random variables. Positive covariance indicates a tendency to vary in the same direction. Negative covariance indicates opposite variation. Zero covariance does not generally imply independence. Independence does imply zero covariance when the required expectations exist. Correlation normalizes covariance by the standard deviations. It lies between -1 and 1 when both standard deviations are positive. Correlation measures linear association. A correlation near 0 does not rule out a strong nonlinear relationship. The Bernoulli distribution models one trial with two outcomes. A common coding uses 1 for success and 0 for failure. The parameter p is the probability of success. The mean is p. The variance is p times 1 minus p. The binomial distribution counts successes in a fixed number of independent Bernoulli trials with constant success probability. Its mean is np. Its variance is np times 1 minus p. The geometric distribution counts trials until the first success under one convention. It has the memoryless property. Given that no successes occurred so far, the conditional distribution of the remaining waiting time is unchanged. The Poisson distribution models counts under an idealized constant rate process with independent increments. Its parameter lambda is both its mean and variance. It often approximates a binomial distribution when the number of trials is large, the success probability is small, and their product remains moderate. The uniform distribution assigns equal density across an interval. The exponential distribution models waiting times in a Poisson process. It is memoryless. Its mean is 1 divided by its rate parameter. Its variance is 1 divided by the square of the rate. The normal distribution has a bell-shaped density. It is determined by its mean and variance. The standard normal distribution has mean 0 and variance 1. The density contains the constant 1 divided by the square root of 2 pi and the exponential of negative x squared divided by 2. Its cumulative distribution function has no elementary closed form. Tables and numerical methods are used. The normal distribution appears because many small independent contributions produce approximately normal sums under broad conditions. This is the central limit phenomenon. The law of large numbers concerns sample averages. Under suitable conditions, the average of many independent observations approaches the expected value. The weak law gives convergence in probability. The strong law gives almost sure convergence. These results do not state that short runs must resemble theoretical probabilities closely. They describe long-run behavior. The central limit theorem describes fluctuations around the mean. For independent identically distributed variables with finite non-zero variance, the properly centered and scaled sample sum approaches a standard normal distribution in distribution. This allows approximate confidence intervals in probability calculations. There are many generalizations for dependent, non-identical, or higher dimensional variables. The theorem does not mean that every dataset is normally distributed. It describes the limiting distribution of normalized sums under specified conditions. Conditional expectation generalizes ordinary expectation after information is given. It is itself a random variable. It represents the best mean-square prediction based on the available information. The law of total expectation states that the expectation of a conditional expectation equals the original expectation. The law of total variance decomposes variance into expected conditional variance plus the variance of the conditional mean. Martingale's model FAIR processes relative to evolving information. A martingale has the property that the conditional expectation of the next value given the present information equals the current value. Martingale theory is central to stochastic processes, finance, probability inequalities, and modern analysis. Optional stopping asks when the expected value remains unchanged at a random stopping time. The result requires conditions. A gambling strategy cannot generally defeat a fair game merely by choosing a clever stopping rule. Markov processes have the property that the conditional distribution of the future depends on the present state, not on the full past given the present. Brownian motion is a continuous time stochastic process with continuous paths, independent increments, and normally distributed changes. It begins at 0. The increment over a time interval of length t has mean 0 and variance t in the standard model. Brownian motion is continuous but almost surely nowhere differentiable. It models diffusion and appears in finance, physics, and stochastic calculus. Stochastic calculus defines integration with respect to Brownian motion. The Ito integral differs from ordinary Riemann integration. Its construction uses adapted processes and mean-square limits. Ito's formula is a stochastic analog of the chain rule. It contains an additional second derivative term because Brownian increments have quadratic variation. For a sufficiently smooth function of time in Brownian motion, the differential includes a time derivative, a Brownian derivative term, and 1/2 of the second spatial derivative. This correction is essential to stochastic differential equations. Statistics uses probability to reason from data. A population is the full collection of interest. A sample is the observed subset. A parameter is a fixed but unknown population quantity. A statistic is a function of the observed data. An estimator is a statistic used to estimate a parameter. The bias of an estimator is the difference between its expected value and the true parameter. An unbiased estimator has zero bias. Consistency means that the estimator approaches the true parameter as sample size grows. Efficiency compares variability among estimators. Mean-squared error combines variance and squared bias. A likelihood function treats observed data as fixed and parameters as variable. Maximum likelihood estimation selects parameter values that maximize the likelihood. It often has strong, large sample properties. The logarithm of the likelihood is usually easier to optimize. Products become sums. The maximizing parameter remains the same because logarithm is increasing. A confidence interval is produced by a procedure that covers the true parameter with a specified long-run frequency under repeated sampling. A 95% confidence interval does not generally mean that the fixed parameter has a 95% probability of lying in the particular interval after it has been calculated. That probability interpretation belongs to a Bayesian credible interval under a chosen prior and model. A hypothesis test compares data with a null hypothesis. A p-value is the probability, under the null hypothesis and specified model, of obtaining a result at least as incompatible with the null as the observed result, according to the chosen test statistic. It is not the probability that the null hypothesis is true. It is not the probability that the result occurred by chance. The significance level controls the long-run probability of rejecting a true null hypothesis under the model. This is the type 1 error rate. A type 2 error occurs when a false null hypothesis is not rejected. Power is the probability of rejecting the null when a specified alternative is true. Increasing sample size usually increases power. Regression models the relationship between an outcome and one or more predictors. Simple linear regression uses a line. The model writes the outcome as an intercept plus a slope times the predictor plus an error term. Ordinary least squares chooses coefficients minimizing the sum of squared residuals. Under standard assumptions, the estimator has useful properties. The Gauss-Markov theorem states that ordinary least squares is the best linear unbiased estimator among linear unbiased estimators when the assumptions hold. Normal errors are not required for this theorem. They are often added for exact small sample inference. Multiple regression includes several predictors. Categorical variables can be represented using indicator variables. Interactions allow the effect of one predictor to depend on another. Polynomial terms allow curved mean relationships while remaining linear in the coefficients. Overfitting occurs when a model adapts too closely to training data and performs poorly on new data. Regularization adds a penalty to the objective. Ridge regression penalizes the sum of squared coefficients. Lasso regression penalizes the sum of absolute coefficient values. Ridge shrinks coefficients smoothly. Lasso can set some coefficients exactly to 0. Cross-validation estimates predictive performance by repeatedly dividing data into training and validation subsets. A model is fitted on one part and evaluated on another. The procedure helps select tuning parameters and compare models. Care is needed with time series, group data, and pre-processing. Information from the validation set must not leak into model fitting. We will now move toward deeper foundations. Set theory provides a language for collections. A set is a collection of distinct objects. The objects are called elements. Membership is written using a special symbol, meaning belongs to. Two sets are equal when they contain exactly the same elements. A subset contains only elements of another set. The empty set contains no elements. The union of two sets contains elements belonging to at least one of them. The intersection contains elements belonging to both. The difference contains elements in one set but not the other. The complement contains elements outside a set relative to a specified universal set. The Cartesian product of two sets is the set of ordered pairs formed from their elements. Relations are subsets of Cartesian products. Functions are special relations with exactly one output for each input. An equivalence relation is reflexive, symmetric, and transitive. It divides a set into equivalence classes. Examples include equality, congruence modulo an integer, and similarity under certain transformations. An order relation organizes elements by comparison. A partial order is reflexive, antisymmetric, and transitive. Not every pair must be comparable. A total order requires every pair to be comparable. The real numbers have a total order. Subsets ordered by inclusion form a partial order. Cardinality measures the size of a set. Finite sets have natural number cardinalities. Infinite sets require more subtle comparison. Two sets have the same cardinality when there is a bijection between them. The natural numbers and integers have the same cardinality. A bijection can list the integers in a sequence. The rational numbers are also countable. They can be arranged through a diagonal enumeration with duplicates removed. The real numbers are uncountable. Cantor's diagonal argument proves that no list can contain every real number in an interval. Given any proposed list of decimal expansions, a new number can be constructed that differs from the nth listed number in its nth decimal place. The new number is not on the list. Therefore, the list was incomplete. The cardinality of the real numbers is strictly larger than the cardinality of the natural numbers. Cantor's theorem states that the power set of any set has greater cardinality than the original set. The power set is the set of all subsets. This result creates an endless hierarchy of larger infinities. Mathematical logic studies valid reasoning and formal systems. A proposition is a statement that is either true or false within a given interpretation. Logical connectives include not, and, or, implication, and equivalence. An implication is false only when its premise is true and its conclusion is false. A universally quantified statement claims that a property holds for every element of a domain. An existential statement claims that at least one element has the property. Negating a universal statement produces an existential statement with the property negated. Negating an existential statement produces a universal statement with the property negated. A direct proof begins with assumptions and derives the conclusion. A proof by contrapositive proves that if the conclusion is false, then the premise must be false. A proof by contradiction assumes the desired conclusion is false and derives an impossibility. Mathematical induction proves statements indexed by natural numbers. It establishes a base case, then it proves that truth at one stage implies truth at the next. Strong induction allows the next stage to use all previous cases. Induction is closely related to the recursive structure of the natural numbers. An axiom is a starting statement accepted within a formal system. A theorem is derived from axioms and earlier results using rules of inference. A formal system distinguishes syntax from semantics. Syntax concerns permitted symbols and derivations. Semantics concerns meaning and truth in models. Gödel's completeness theorem for first-order logic states that every logically valid first-order statement has a formal proof. Gödel's incompleteness theorems concern sufficiently expressive formal systems capable of arithmetic. Under standard consistency and effective axiomatization assumptions, such a system contains statements that cannot be proved or disproved within the system. A sufficiently strong consistent system cannot prove its own consistency by its internal methods. These results do not mean that all mathematics is uncertain. They describe precise limitations of formal axiomatic systems. The standard foundation of much modern mathematics is set theory with the Zermelo-Fraenkel axioms, often including the axiom of choice. The axiom of choice states, in one form, that for any collection of non-empty sets, there exists a function selecting one element from each set. It has many equivalent formulations. One is Zorn's lemma. Another is the well-ordering theorem. The axiom of choice is useful and widely accepted, though some of its consequences are counterintuitive. The Banach-Tarski paradox is one such consequence. It states that a solid ball in three-dimensional space can be decomposed into finitely many highly non-measurable pieces and reassembled using rotations and translations into two balls of the original size. The pieces are not ordinary physical solids. They are non-measurable sets. The result does not describe a physically realizable process. Topology studies properties preserved by continuous deformation. A topological space consists of a set and a collection of open sets, satisfying certain axioms. The empty set and entire space are open. Arbitrary unions of open sets are open. Finite intersections of open sets are open. The open sets define concepts such as continuity, convergence, neighborhoods, interior, closure, and boundary. In metric spaces, open sets can be defined using open balls. An open ball contains points within a specified distance from a center. Not every topological space comes from a metric. Continuity has a topological definition. A function is continuous when the inverse image of every open set is open. This definition generalizes epsilon delta continuity. It works without coordinates or numerical distance. A homomorphism is a continuous bijection with a continuous inverse. Homomorphic spaces are considered topologically equivalent. A circle and a square boundary are homomorphic. A sphere and the surface of a cube are homomorphic. A circle is not homeomorphic to a line. Removing one point from a circle leaves a connected interval-like space. Removing one point from a line leaves two disconnected components. Connectedness means that a space cannot be separated into two disjoint non-empty open subsets. Path connectedness means that any 2 points can be joined by a continuous path. Path connectedness implies connectedness. The converse is not always true. Compactness is another central property. An open cover is a collection of open sets whose union contains the space. A compact space is one in which every open cover has a finite subcover. In Euclidean space, compact sets are exactly the closed and bounded sets. This is the Heine-Borel theorem. Continuous images of compact sets are compact sets. A continuous real-valued function on a compact space reaches its maximum and minimum. Compactness often replaces finiteness in analysis. It allows global conclusions from local information. A sequence in a compact metric space has a convergent subsequence. This is sequential compactness. In metric spaces, compactness and sequential compactness are equivalent. In general topological spaces, the relationship is more complicated. Hausdorff spaces separate distinct points with disjoint neighborhoods. Limits are unique in Hausdorff spaces. Compact subsets of Hausdorff spaces are closed. Most familiar spaces in analysis are Hausdorff. A manifold is a space that locally resembles Euclidean space. A curve is locally one-dimensional. A surface is locally two-dimensional. Higher dimensional manifolds are locally two-dimensional. Higher dimensional manifolds are locally modeled on higher dimensional coordinate spaces. Manifolds allow calculus on curved spaces. Charts provide local coordinates. Atlases combine compatible charts. Differentiable manifolds support derivatives and tangent spaces. Riemannian manifolds add an inner product on each tangent space that varies smoothly. This structure defines lengths, angles, areas, volumes, and geodesics. A geodesic is a locally shortest or locally straightest path. On a plane, geodesics are straight lines. On a sphere, they are great circles. Curvature measures how geometry differs from flat Euclidean geometry. Gaussian curvature is intrinsic to a surface. It can be determined from measurements made entirely within the surface. The sphere has positive Gaussian curvature. A plane has zero curvature. A saddle-shaped surface has negative curvature near the saddle point. Riemann extended these ideas to higher dimensions. Einstein's general theory of relativity later used pseudo-Riemannian geometry to describe space-time and gravitation. Algebra studies abstract operations in structure. A group is a set with one binary operation satisfying closure, associativity, the existence of an identity, and the existence of inverses. The operation need not be commutative. If it is commutative, the group is called abelian. The integers under addition form an abelian group. Non-zero real numbers under multiplication form an abelian group. Permutations of the set form a group under composition. Matrix multiplication gives groups of invertible matrices. Groups describe symmetry. The symmetries of a geometric object form a group. The rotations of a square, together with its reflections, form the dihedral group of order 8. The order counts the number of group elements. A subgroup is a subset that is itself a group under the same operation. A cyclic group is generated by repeated application of one element and its inverse. The integers under addition form an infinite cyclic group generated by 1 or -1. A homomorphism is a structure-preserving map between groups. Its kernel consists of elements mapped to the identity. Its image is a subgroup of the target. The first isomorphism theorem relates the original group, the kernel, and the image. Quotient groups identify elements that differ by a normal subgroup. Normality is required so that coset multiplication is well defined. Rings have two operations resembling addition and multiplication. The integers form a ring. Polynomial sets form rings. Matrices form non-commutative rings. A field is a commutative ring in which every non-zero element has a multiplicative inverse. Fields support linear algebra and polynomial theory. Ideals are special subsets of rings that absorb multiplication by ring elements. They play a role similar to normal subgroups. Quotient rings are formed using ideals. Prime and maximal ideals generalize prime numbers and support algebraic geometry. A vector space is also a module over a field. Modules generalize vector spaces by allowing scalars from a ring. Without division by every non-zero scalar, module structure can be more complicated. Bases may not exist. Submodules may behave differently from vector subspaces. Field extensions enlarge fields by adding new elements. The complex numbers can be viewed as an extension of the real numbers. The field of rational numbers can be extended by adjoining the square root of 2. Galois theory studies field extensions and their symmetries. It connects polynomial solvability with group structure. A general polynomial of degree 5 or higher cannot be solved by radicals. This does not mean that no fifth-degree equation has a radical solution. It means there is no universal radical formula for all quintic equations analogous to the quadratic formula. The obstruction is explained by the non-solvability of certain Galois groups. Évariste Galois developed these ideas in the early 19th century. His work linked equations with symmetry in a profound way. Number theory studies properties of integers. A prime number is a positive integer greater than 1 with exactly 2 positive divisors. Every integer greater than 1 can be written as a product of primes. The factorization is unique apart from order. This is the fundamental theorem of arithmetic. Euclid proved that there are infinitely many primes. Assume only finitely many primes exist. Multiply them all and add 1. The resulting number is not divisible by any prime on the supposed complete list. It is either prime or has a prime factor not on the list. This gives a contradiction. The greatest common divisor of two integers is the largest positive integer, dividing both. The Euclidean algorithm computes it efficiently. Repeatedly replace the larger pair by the divisor and remainder. The process ends when the remainder becomes 0. The last non-zero remainder is the greatest common divisor. The extended Euclidean algorithm expresses the greatest common divisor as an integer linear combination of the original numbers. Congruence arithmetic studies remainders. The statement A is congruent to B modulo n means that n divides A minus B. Congruence is an equivalence relation. The integers split into residue classes modulo n. Addition and multiplication are compatible with congruence. This creates modular arithmetic. Fermat's little theorem states that if p is prime and a is not divisible by p, then a to the power p minus 1 is congruent to 1 modulo p. Euler's theorem generalizes this using Euler's totient function. The totient counts positive integers up to n that are relatively prime to n. If a and n are relatively prime, then a to the power phi of n is congruent to 1 modulo n. These results support public key cryptography. The RSA cryptosystem uses multiplication of large primes, modular exponentiation, and the difficulty of factoring large composite integers. Its security depends on key size, implementation, padding, and current computational methods. It does not rely merely on numbers being large in an informal sense. The distribution of primes is irregular but has strong average behavior. The prime number theorem states that the number of primes less than or equal to x is approximately x divided by the natural logarithm of x for large x. The ratio of the two quantities approaches 1. The Riemann zeta function is initially defined by a series of reciprocal powers. For complex S with real part greater than 1, zeta of S equals the sum of 1 divided by n to the power S. Euler showed that it also equals a product over primes. This Euler product connects the zeta function with prime numbers. The function can be extended analytically to most of the complex plane with a simple pole at 1. Its non-trivial zeros lie in a critical strip. The Riemann hypothesis states that every non-trivial zero has real part 1/2. It remains unproved. It has deep consequences for the precision of estimates involving prime distribution. Complex analysis studies functions of a complex variable. A complex function is differentiable at a point only if the same derivative is obtained from every direction in the complex plane. This condition is much stronger than real differentiability. A complex function differentiable throughout an open region is called holomorphic. Holomorphic functions are infinitely differentiable and analytic. They locally equal convergent power series. The Cauchy-Riemann equations relate the real and imaginary parts of a complex differentiable function. If f of z equals u of x and y plus I times v of x and y, then under suitable regularity conditions, u sub x equals v sub y and u sub y equals negative v sub x. Complex integration follows curves in the complex plane. Cauchy's integral theorem states that the integral of a holomorphic function around a closed contour is 0 under appropriate domain conditions. Cauchy's integral formula expresses the value of a holomorphic function inside a contour, using its values on the contour. This formula implies strong rigidity. A holomorphic function is determined throughout a connected domain by its behavior on any small open subset. Liouville's theorem states that every bounded entire function is constant. An entire function is holomorphic on the whole complex plane. The fundamental theorem of algebra follows from Liouville's theorem. If a non-constant polynomial had no complex roots, its reciprocal would be a bounded entire function. Liouville's theorem would force the reciprocal, and therefore the polynomial, to be constant. Singularities are points where a complex function fails to be holomorphic. An isolated singularity may be removal, a pole, or essential. A removal singularity can be filled in to make the function holomorphic. A pole is a controlled form of divergence. An essential singularity has more complicated behavior. The Laurent series extends power series by allowing negative powers. The coefficient of the negative first power is the residue. The residue theorem relates contour integrals to sums of residues inside the contour. It is a powerful method for evaluating real and complex integrals. Complex analysis also explains conformal maps. A holomorphic function with non-zero derivative preserves angles locally. Conformal mappings transform complicated regions into simpler ones while preserving local angular geometry. They are used in fluid mechanics, electrostatics, and geometry. Functional analysis studies infinite-dimensional vector spaces and operators. A normed space is a vector space with a norm. A Banach space is complete under the metric induced by its norm. Completeness means that every Cauchy sequence converges within the space. A Hilbert space is a complete inner product space. Euclidean space is a finite-dimensional Hilbert space. Space of square integrable functions are infinite-dimensional Hilbert spaces. Orthogonality, projection, and Fourier expansion extend naturally to Hilbert spaces. An operator maps one function or vector to another. Differentiation is an operator. Integration is an operator. Matrices are finite-dimensional operators. A bounded linear operator is continuous. The operator norm measures its maximum stretching. The Hahn-Banach theorem extends linear functionals under norm constraints. The open mapping theorem states that a surjective bounded linear operator between Banach spaces maps open sets to open sets. The closed graph theorem gives conditions under which a linear operator is bounded. The uniform boundedness principle converts pointwise boundedness of a family of operators into a uniform norm bound. These results are sometimes called the major principles of functional analysis. Spectral theory generalizes eigenvalue analysis. In infinite-dimensional spaces, an operator may have continuous spectrum as well as eigenvalues. Compact operators behave in some ways like matrices. Their non-zero spectrum consists of eigenvalues with finite multiplicity, with possible accumulation only at zero. Self-adjoint operators on Hilbert spaces have real spectrum. They are central to quantum mechanics. Measure theory provides a general foundation for integration. A sigma algebra is a collection of subsets closed under complements and countable unions. A measure assigns non-negative size to measurable sets and is countably additive. Length, area, volume, and probability are examples of measures. The Lebesgue integral extends the Riemann integral. Instead of partitioning the domain into intervals, it can be understood as organizing points according to function values. It integrates a broader class of functions. It also behaves well under limits. The monotone convergence theorem allows the limit of an increasing sequence of non-negative measurable functions to pass through the integral. Fautout's lemma gives an inequality involving the integral of a lower limit. The dominated convergence theorem allows limits and integrals to be exchanged when functions are dominated by an integrable bound. These theorems are fundamental in analysis and probability. A set of measure zero is negligible for integration. Changing a function on a measure zero set does not change its Lebesgue integral. Functions equal except on a null set are treated as equivalent in many function spaces. The space LP consists of functions whose Bth absolute power is integrable, with functions identified when they differ only on a null set. For P at least 1, LP is a Banach space. The space L2 is a Hilbert space. The dual relationship between LP and LQ uses exponents satisfying 1 divided by P plus 1 divided by Q equals 1. Hutter's inequality and Minkowski's inequality generalize Cauchy-Schwarz and the triangle inequality. Differential geometry, topology, algebra, analysis, and probability eventually intersect. Modern mathematics often studies not isolated formulas but structures and maps between structures. Category theory makes this viewpoint explicit. A category contains objects and morphisms between objects. Morphisms can be composed. Composition is associative. Each object has an identity, morphism. Sets and functions form a category. Groups and homomorphisms form a category. Topological spaces and continuous maps form a category. Vector spaces and linear transformations form a category. A functor maps one category to another while preserving identities and composition. A natural transformation compares functors. Category theory focuses on relationships that remain meaningful across different mathematical settings. It can reveal that constructions in apparently separate fields share the same abstract form. Homology and cohomology assign algebraic objects to topological spaces. They detect wholes of different dimensions. The zero-dimensional homology records connected components. The first homology detects loop-like holes. The second detects cavity-like structures. These invariants help distinguish spaces that may otherwise appear similar. Homotopy studies continuous deformation of maps. The fundamental group records loops up to continuous deformation. A simply connected space has no non-trivial loop obstruction. A circle has fundamental group isomorphic to the integers. A sphere of dimension at least 2 has trivial fundamental group. The torus has a fundamental group reflecting 2 independent loop directions. Algebraic topology converts geometric questions into algebraic calculations. It also returns algebraic results to geometry. The boundaries between mathematical subjects are therefore not fixed. Linear algebra enters calculus through derivatives. Calculus enters probability through densities and expectations. Probability enters analysis through measure. Algebra enters geometry through symmetry. Topology enters differential equations through global structure. Number theory enters cryptography and algebraic geometry. Fourier analysis links differential equations, harmonic analysis, signal processing, and representation theory. At a deeper level, Higher mathematics is organized by a small collection of recurring ideas. One idea is approximation. A nonlinear function is approximated by a tangent line. A smooth function is approximated by a polynomial. A complicated signal is approximated by Fourier modes. A high-dimensional dataset is approximated by a lower-rank matrix. A differential equation is approximated by discrete numerical steps. Another idea is invariance. A quantity is useful when it remains unchanged under a class of transformations. Distance is invariant under rigid motion. Determinant measures oriented volume scaling. Eigenvalues remain unchanged under a change of basis. Topological invariants remain unchanged under homomorphism. Probabilities remain consistent under different representations of the same event structure. Another idea is decomposition. Integers decompose into prime factors. Vectors decompose into basis components. Matrices decompose into triangular, orthogonal, or singular value factors. Functions decompose into Fourier modes. Representations decompose into irreducible components. Space decompose into simpler pieces. A further idea is completeness. The real numbers are complete. Banach spaces are complete. Hilbert spaces are complete. Hilbert spaces are complete. Completeness allows limiting processes to remain inside the space under study. Without it, Cauchy sequences may point toward missing objects. The rational numbers are not complete. A rational sequence can approach the square root of 2 without converging to any rational number. Completing the rationals produces the real numbers. Completing an inner product space produces a Hilbert space. Another recurring idea is duality. Points can be studied through functions. Vectors can be studied through lengtheners. Vectors can be studied through linear functionals. Optimization problems have dual formulations. Geometry and algebra reflect one another. Time and frequency descriptions are related by Fourier transform. Differential forms in chains pair through integration. Duality often converts a difficult question into a more manageable one. Symmetry is another central idea. Groups formalize symmetry. Conservation laws arise from continuous symmetries in physical systems. Noether's theorem states that differentiable symmetries of an action correspond to conservation laws under suitable conditions. Time translation symmetry corresponds to conservation of energy. Spatial translation symmetry corresponds to conservation of momentum. Rotational symmetry corresponds to conservation of angular momentum. The theorem belongs to the calculus of variations in mathematical physics. The calculus of variations optimizes entire functions rather than finite-dimensional vectors. A functional assigns a number to a function. For example, the length of a curve is a functional. The action in mechanics is a functional of a trajectory. A stationary function makes the first variation vanish. The Euler-Lagrange equation provides a necessary condition. If a functional is the integral of a Lagrangian depending on position, derivative, and the independent variable, then the derivative of the partial derivative with respect to the velocity-like term minus the partial derivative with respect to the position-like term equals 0. Classical mechanics can be formulated through this equation. The path taken by a system makes the action stationary. The same framework appears in optics, geometry, control theory, and field theory. Convex analysis studies functions and sets with no inward dents. A set is convex when the line segment between any two of its points lies entirely within the set. A function is convex when its graph lies below the chord joining any 2 points on the graph. For differentiable convex functions, every local minimum is global. For strictly convex functions, the global minimum is unique when it exists. The Hessian of a twice differentiable convex function is positive, semi-definite. Convex optimization is especially tractable. Duality, separating hyperplanes and subgradients, provides strong theory. Non-differentiable convex functions can still be optimized using subgradients. Linear programming optimizes a linear objective over linear constraints. The feasible region is a convex polyhedron. When an optimum exists under standard finite dimensional conditions, at least one optimum occurs at an extreme point. The simplex method moves among extreme points. Interior point methods travel through the interior. Linear programming duality pairs every primal problem with a dual problem. Weak duality gives a bound. Strong duality gives equality of optimal values under appropriate conditions. Integers programming requires some or all variables to take integer values. This usually makes problems much harder. Many integer optimization problems are computationally intractable in the worst case. Complexity theory classifies computational problems by required resources. The class P contains decision problems solvable in polynomial time by a deterministic algorithm. The class NP contains problems whose proposed solutions can be verified in polynomial time. Every problem in P belongs to NP. Whether P equals NP remains unknown. An NP-complete problem is in NP and at least as hard as every problem in NP under polynomial time reductions. If any NP-complete problem has a polynomial time solution, then P equals NP. The Boolean satisfiability problem was the first problem proved NP-complete. Many scheduling, routing, packing, and graph problems have NP-complete forms. Computability theory asks what can be computed at all. A Turing machine is an abstract model of computation. The Church-Turing thesis states that every effectively calculable function can be computed by a Turing machine or an equivalent formal model. It is a thesis about the concept of effective computation, not a theorem derived inside one formal system. The halting problem asks whether an arbitrary program eventually stops on a given input. No algorithm can correctly solve this problem for all programs and inputs. The proof uses self-reference and contradiction. There are therefore well-defined computational questions that no universal algorithm can decide. Numerical analysis studies approximate computation with finite resources. Real numbers are usually represented with finite precision. Floating-point arithmetic stores a sign, exponent, and significand. Most real numbers cannot be represented exactly. Rounding errors are unavoidable. A numerically stable algorithm controls how errors propagate. A problem is well-conditioned when small input changes produce small output changes. An algorithm may be unstable even for a well-conditioned problem. A condition number measures sensitivity. For solving a linear system, a large matrix condition number indicates that small data or rounding errors may produce large solution errors. Backward error analysis asks whether the computed result is the exact solution to a nearby problem. This is often more informative than measuring only forward error. Iterative methods solve large linear systems without direct factorization. The Jacobi and Gauss-Seidel methods use repeated updates. Conjugate gradient applies to symmetric positive definite systems. It minimizes a quadratic function over expanding Krylov subspaces. In exact arithmetic, it terminates in at most n steps for an n-dimensional system. In practical floating-point work, convergence depends on eigenvalue distribution and conditioning. Preconditioning transforms a system into an equivalent one that is easier to solve iteratively. Numerical solutions of differential equations also require stability analysis. Euler's method approximates the next value using the current slope. For y prime equals f of t and y, the update is y sub n plus 1 equals y sub n plus 1 equals y sub n plus h times f of t sub n and y sub n. The local truncation error is proportional to h squared. The accumulated global error is proportional to h under suitable assumptions. Runge-Kutta methods use several slope evaluations per step. The classical fourth-order method has global error proportional to h to the fourth power under suitable smoothness. Multi-step methods use several previous points. Implicit methods require solving equations at each step but can be more stable for stiff problems. A stiff differential equation contains processes evolving at very different timescales. Explicit methods may require extremely small steps for stability, even when the desired solution changes slowly. Implicit methods such as backward Euler can take larger stable steps. For partial differential equations, discretization may use finite differences, finite volumes, spectral methods, or finite elements. Finite differences replace derivatives with differences on a grid. Finite volumes enforce conservation across cell boundaries. Finite elements approximate solutions using basis functions on a mesh. Spectral methods use global basis functions and can achieve very high accuracy for smooth solutions. Discretization converts a continuous problem into a finite algebraic system. Consistency, stability, and convergence are linked. For certain linear initial value problems, the Lax equivalence theorem states that a consistent finite difference scheme is convergent if and only if it is stable. The finite element method begins with a weak formulation. Derivatives are transferred through integration by parts. This reduces regularity requirements. The solution is approximated in a finite dimensional function space, often using piecewise polynomials. Mesh refinement improves spatial resolution. Adaptive methods concentrate computational effort where the estimated error is largest. Modern higher mathematics also includes information theory. Information theory quantifies uncertainty and communication. The entropy of a discrete random variable is the negative sum of probabilities times their logarithms. The logarithm base determines the unit. Base 2 gives bits. Entropy is largest for a uniform distribution on a finite set. It is 0 when one outcome has probability 1. Conditional entropy measures remaining uncertainty after another variable is known. Mutual information measures shared information. It is 0 exactly when the variables are independent under the usual definitions. The data processing inequality states that processing data cannot increase information about an earlier variable when the variables form a Markov chain. Kullback-Leibler divergence measures discrepancy between probability distributions. It is non-negative. It is generally not symmetric. It does not satisfy the triangle inequality. Therefore, it is not a true metric. Shannon's source coding theorem relates entropy to the minimum average length of lossless codes. The noisy channel coding theorem gives a channel capacity below which reliable communication is possible. In principle, coding theory constructs representations that detect or correct errors. Linear codes use vector spaces over finite fields. A code word is transmitted through a noisy channel. The received word may differ in some positions. Hamming distance counts differing coordinates. A code with sufficiently large minimum distance can detect and correct bounded numbers of errors. Finite fields contain a finite number of elements. A finite field exists exactly when the number of elements is a prime power. For each prime power, there is a finite field unique up to isomorphism. Finite fields support coding theory, cryptography, and combinatorics. Combinatorics studies discrete structures in counting. The addition principle applies to disjoint alternatives. The multiplication principle applies to sequential choices. The number of permutations of n distinct objects is n factorial. The number of ways to choose k objects from n without order is the binomial coefficient n choose k. It equals n factorial divided by k factorial times n minus k factorial. The binomial theorem expands a plus b to the power n using binomial coefficients. Pascal's identity relates adjacent coefficients. The pigeonhole principle states that if more objects than containers are distributed among the containers, at least one container holds more than one object. Its generalized form gives a lower bound on maximum occupancy. Simple as it appears, the principle proves many non-trivial existence results. Inclusion-exclusion counts the size of a union by alternating sums of intersections. For two sets, add their sizes and subtract the size of their intersection. For three sets, add individual sizes, subtract pairwise intersections, and add the triple intersection. The pattern continues. Generating functions encode sequences as power series. Operations on generating functions, correspond to operations on sequences. They solve recurrence relations and counting problems. Ordinary generating functions use coefficients of x to the power n. Exponential generating functions divide coefficients by n factorial. Different forms suit different combinatorial structures. Graph theory studies vertices and edges. A graph may represent roads, social links, dependencies, molecules, or communication networks. A path is a sequence of connected edges. A cycle returns to its starting vertex without repeating intermediate vertices in the simple case. A graph is connected when every pair of vertices is joined by a path. A tree is a connected graph with no cycles. A tree with n vertices has n-1 edges. Between any two vertices of a tree, there is exactly one simple path. A spanning tree connects every vertex using a subset of edges and contains no cycles. Weighted graphs assign costs or length to edges. A minimum spanning tree has the least total weight. Kruskal's algorithm adds edges in increasing weight order while avoiding cycles. Prim's algorithm grows one connected tree by repeatedly adding the cheapest available connecting edge. Shortest path problems seek minimum cost routes. Dijkstra's algorithm works when edge weights are non-negative. The Bellman-Ford algorithm allows negative edges and can detect reachable negative cycles. The Floyd-Warshall algorithm computes shortest paths between all pairs using dynamic programming. Network flow studies movement through capacity-constrained edges. The maximum flow minimum cut theorem states that the largest feasible flow from source to sink equals the smallest capacity of a cut separating them. This duality has applications in routing, matching, scheduling, and image segmentation. A bipartite graph divides vertices into two sets, with edges only between sets. A matching selects edges with no shared endpoints. Hall's marriage theorem gives a condition for a matching that covers one side of a bipartite graph. The condition compares every subset with its set of neighbors. Planar graphs can be drawn without crossing edges. Euler's formula states that for a connected planar graph, the number of vertices minus the number of edges plus the number of faces equals 2. This leads to restrictions on planar graphs. The complete graph on 5 vertices is non-planar. The complete bipartite graph with 3 vertices on each side is also non-planar. Kuratowski's theorem characterizes planar graphs through subdivisions of these two graphs. The 4-color theorem states that every planar map can be colored with at most 4 colors, so that adjacent regions have different colors. Its accepted proof used extensive computer assistance. This raised important questions about the nature of proof verification, though computer-assisted proofs are now common in several fields. At this point, the course has moved from elementary number systems to broad structures. A deeper understanding does not mean memorizing every theorem. It means recognizing how definitions control what can be proved. It means distinguishing examples from general principles. It means seeing that conditions in a theorem are part of the theorem, not decorative details. Continuity on a closed interval differs from continuity on an open interval. Independence differs from zero correlation. Differentiability differs from continuity. Pointwise convergence differs from uniform convergence. Existence differs from uniqueness. Exact computation differs from stable approximation. Finite-dimensional intuition sometimes extends to infinite dimensions and sometimes fails. A mature mathematical approach begins by identifying the objects. One asks what set they belong to. One identifies the operations. One states the assumptions. One selects an appropriate notion of convergence, distance, equivalence, or structure. Only then does calculation begin. Proof and computation support each other. Computation suggests patterns. Proof explains why a pattern must hold and states the exact domain where it holds. Counterexamples show why weaker assumptions are insufficient. A single counterexample disproves a universal statement. No number of confirming examples proves a universal statement by itself. Mathematical models are not the systems they describe. A model selects variables and relationships. It omits details. Its conclusions depend on assumptions, parameter estimates, and the range where the model is valid. A linear approximation is local. An exponential growth law may fail when resources become limited. A normal approximation may fail in heavy-tailed data. An equilibrium may be mathematically stable but physically unreachable. A numerical answer may be precise in digits but inaccurate in meaning. Understanding therefore includes interpretation. Units must remain consistent. Domains must be rechecked. Singular points must be examined. Boundary and initial conditions must be stated. Approximation error must be considered. Statistical uncertainty must not be confused with deterministic error. Correlation must not be interpreted automatically as causation. An optimal solution must be understood relative to the chosen objective and constraints. The deepest unifying language in mathematics is often the language of maps. A derivative is a local linear map. A matrix represents a linear map. A probability distribution maps events to numbers. A measure maps measurable sets to sizes. A homomorphism maps algebraic structures while preserving operations. A continuous function maps nearby points to nearby outputs in a topological sense. A functor maps mathematical structures and their relationships into other structures. Studying an object often means studying the maps into it and out of it. Another unifying language is that of limits. Real numbers complete the rationals through limits. Derivatives are limits of difference, quotients. Integrals are limits of sums. Infinite series are limits of partial sums. Probability laws emerge through limiting behavior. Numerical algorithms are judged by convergence as resolution improves. Function spaces are completed through limits of Cauchy sequences. Weak solutions are limits of smoother approximations. A limit is not simply a value reached after infinitely many steps. It is a statement about arbitrary accuracy. It says that errors can be controlled beyond a suitable stage. This is why epsilon-based definitions are central. They transform intuitive closeness into logical quantifiers. For every required accuracy, there exists a threshold after which the condition holds. The same pattern appears throughout analysis. Uniform estimates strengthen pointwise estimates. Compactness allows infinitely many local conditions to be reduced to finitely many choices. Completeness guarantees that approximating sequences have destinations inside the space. The higher course of mathematics is therefore not a straight ladder, it is a network. Arithmetic leads to algebra, algebra leads to functions. Functions lead to limits. Limits lead to calculus. Calculus leads to differential equations and analysis. Linear algebra intersects every stage. Set theory and logic provide foundations. Topology studies continuity without formulas. Abstract algebra studies operations without specific numbers. Probability adds uncertainty. Numerical analysis connects exact theory with finite computation. Geometry gives space and curvature. Combinatorics studies discrete form. Each branch returns to the others with new language. There is still more depth beyond these foundations. One may continue into distribution theory, ergodic theory, operator algebras, algebraic geometry, representation theory, stochastic analysis, geometric measure theory, model theory, symplectic geometry, nonlinear functional analysis, and many other areas. Each field begins with definitions. Each develops examples and counterexamples. Each identifies invariants. Each proves existence, uniqueness, classification, approximation, or impossibility results. The same habits remain useful. State the domain. Track the assumptions. Separate local behavior from global behavior. Distinguish finite from infinite processes. Test whether operations commute. Check whether a limit exists and in what sense. Identify the structure preserved by the transformation. Determine whether an object is exact, approximate, random, or deterministic, and allow every conclusion to remain precisely as strong as the premises permit. In advanced mathematics, one also learns that the form of an answer depends on the form of the question. A problem may ask for an exact value. It may ask for an approximation. It may ask whether a solution exists. It may ask whether the solution is unique. It may ask how the solution changes when the data change. It may ask whether a procedure terminates. It may ask whether a theorem remains true after one assumption is removed. These are different mathematical tasks. They require different methods. An existence proof may provide no practical way to construct the object. A constructive proof gives a procedure, at least in principle. A uniqueness proof shows that no second object can satisfy the same conditions. A stability result shows that small perturbations do not create large changes. A classification theorem describes all objects of a specified type. An impossibility theorem establishes that no object or algorithm with certain properties can exist. Mathematics advances through all of these forms. We may now examine convergence more deeply. Earlier, convergence was described for sequences of numbers. In higher analysis, one studies sequences of functions. A sequence of functions may converge in several different senses. These senses are not interchangeable. Pointwise convergence means that for each fixed input, the sequence of function values converges. The stage at which the values become close may depend on the chosen input. Uniform convergence requires one stage that works simultaneously for every input in the domain. More precisely, a sequence f sub n converges uniformly to f if, for every positive epsilon, there exists an n such that the absolute value of f sub n of x minus f of x is less than epsilon for every x in the domain whenever n is at least n. The crucial point is that n does not depend on x. Uniform convergence preserves several properties that pointwise convergence may fail to preserve. A uniform limit of continuous functions is continuous. A pointwise limit of continuous functions need not be continuous. For example, on the interval from 0 to 1, consider f sub n of x equals x to the power n. At every x strictly less than 1, the sequence approaches 0. At x equal to 1, every term equals 1. The pointwise limit is therefore 0 on the interval from 0 up to but not including 1, and 1 at the endpoint. This limit is discontinuous. The convergence is not uniform. The maximum difference from the limiting function does not approach 0. Differentiation behaves even more delicately under limits. A sequence of differentiable functions may converge uniformly while the limit is not differentiable. Additional control over the derivatives is required. One useful theorem states that if the derivatives converge uniformly and the original functions converge at one point, then the functions converge uniformly to a differentiable limit whose derivative is the limit of the derivatives. Integration is more stable. If continuous functions converge uniformly on a closed interval, their integrals converge to the integral of the limit. Measure theory offers stronger convergence theorems for less regular functions. Convergence in measure means that the set where the error exceeds a chosen tolerance has measure approaching 0. Convergence almost everywhere means that convergence occurs at every point except possibly on a set of measure 0. Convergence in an LP norm means that the integral of the p power of the absolute error approaches 0. None of these notions is identical in full generality. Under finite measure, convergence in a higher LP space may imply convergence in a lower LQ space under suitable conditions. Almost everywhere, convergence together with domination may imply L1 convergence by the dominated convergence theorem. Convergence in probability is the probabilistic analog of convergence in measure. Almost sure convergence is analogous to almost everywhere convergence. Convergence in distribution is weaker. It requires convergence of distribution functions at continuity points of the limiting distribution. Almost sure convergence implies convergence in probability. Convergence in probability implies convergence in distribution. The reverse implications do not generally hold without additional assumptions. These distinctions matter because a statement about one form of convergence cannot be silently replaced by another. A sequence may converge in distribution while individual realizations do not approach a limiting value. A sequence may converge pointwise while integrals fail to converge as expected. The chosen topology or norm determines what convergence means. This leads to the broad idea that analysis is partly the study of spaces equipped with notions of nearness. A metric space has a distance function. The distance between x and y is non-negative. It equals 0 exactly when x equals y. It is symmetric. It satisfies the triangle inequality. Different metrics may be placed on the same underlying set. They may produce the same open sets or different ones. Two metrics that produce the same topology agree on which sets are open, but they may measure distances differently. On a finite dimensional vector space, all norms are equivalent in the topological sense. They define the same convergent sequences and open sets. This is not generally true in infinite dimensional spaces. The choice of norm can change compactness, convergence, and continuity properties. A Cauchy sequence is a sequence whose terms become arbitrarily close to one another. The definition does not mention a proposed limit. In a complete metric space, every Cauchy sequence converges. Completeness belongs to the space, not merely to an individual sequence. The real numbers are complete. The rational numbers are not. Finite dimensional norm spaces over the real or complex numbers are complete. Many spaces of functions become complete only after identifying functions that differ on sets of measure 0 and choosing an appropriate norm. The contraction mapping theorem is one of the most useful consequences of completeness. A contraction is a map that reduces distances by a fixed factor less than 1. On a complete metric space, a contraction has a unique fixed point. Repeated application of the map from any starting point converges to that fixed point. This theorem proves existence and uniqueness in differential equations, integral equations, numerical iteration, and dynamic programming. It also gives an error estimate. After each iteration, the remaining distance to the fixed point decreases geometrically. The fixed point viewpoint is very general. Solving an equation can often be reformulated as finding x such that t of x equals x. Newton's method is a fixed point iteration. Picard iteration for differential equations is another. Equilibrium in economics can be formulated as a fixed point. Game theory uses fixed point theorems to prove the existence of mixed strategy equilibria. Not every fixed point theorem requires contraction. Brouwer's fixed point theorem states that every continuous map from a compact convex subset of finite dimensional Euclidean space to itself has a fixed point. In a simple case, every continuous map from a closed interval to itself has a fixed point. The higher dimensional theorem is much deeper. It is an existence theorem. It does not generally provide an efficient method for finding the fixed point. Schroeder's fixed point theorem extends the idea to certain infinite dimensional settings. Banach's theorem gives uniqueness under contraction. Brouwer's and Schauer's theorems often give existence without uniqueness. This contrast is typical. Stronger assumptions lead to stronger conclusions. The inverse function theorem describes when a differentiable map can be reversed locally. For a function from n-dimensional space to n-dimensional space, consider its derivative matrix at a point. If the determinant of this Jacobian matrix is non-zero, then the function has a differentiable local inverse near that point. The derivative of the inverse is the inverse of the derivative matrix. The theorem is local. It does not guarantee a global inverse. A function can be locally invertible near every point and still fail to be globally one-to-one. The exponential map from real numbers to the unit circle through sine and cosine is locally invertible but periodic. Different inputs produce the same point. The implicit function theorem explains when an equation can be solved locally for some variables in terms of others. Suppose an equation f of x and y equals 0 is satisfied at a point. If the appropriate partial derivative with respect to y is non-zero, then near that point, y can be expressed as a differentiable function of x. In higher dimensions, an invertible block of the Jacobian provides the condition. The theorem justifies implicit differentiation. It also explains the local geometry of level sets. A regular level set of a smooth function is a manifold. The rank theorem generalizes these ideas. It states that a smooth map of constant rank can be simplified locally by suitable coordinate changes. Near a regular point, the complicated smooth map resembles a projection onto coordinate axes. This is one reason local differential geometry often reduces to linear algebra. The derivative is the best linear approximation. The rank of the derivative determines local dimension. Critical points occur where the rank drops. Their behavior may be studied by singularity theory. Morse theory examines smooth functions whose critical points are non-degenerate. A non-degenerate critical point has an invertible Hessian. Near such a point, a smooth change of coordinates reduces the function to a sum of positive and negative squares plus a constant. The number of negative squares is called the index. As the value threshold passes a critical point, the topology of sublevel sets changes in a controlled way. Morse theory connects derivatives with global topology. It allows information about a manifold to be extracted from the critical points of a function defined on it. Optimization, topology, and dynamical systems meet in this framework. Gradient descent follows the negative gradient direction. In continuous time, the gradient flow satisfies x prime equals negative gradient f of x. Along a smooth gradient flow, the function value decreases unless the gradient is zero. Critical points are equilibria. Local minima can attract nearby trajectories. Saddle points have both attracting and repelling directions. In discrete optimization, gradient descent uses steps of finite size. The step size affects convergence. If the gradient is Lipschitz continuous and the step is sufficiently small, the objective decreases under standard assumptions. For a strongly convex function, gradient descent converges at a geometric rate. For a general convex smooth function, the rate is slower. Accelerated methods can improve the theoretical rate. Newton's optimization method uses the Hessian. It approximates the function quadratically and solves for the stationary point of that approximation. Near a non-degenerate optimum, convergence can be very rapid. Far from the optimum, the method may fail without line search, damping, or trust region control. Quasi-Newton methods approximate the Hessian or its inverse using gradient information. The BFGS method is a common example. Limited memory variants are useful in high dimensions. Optimization also distinguishes constrained and unconstrained problems. Equality constraints define surfaces. Inequality constraints define feasible regions with boundaries. The Karush-Kuhn-Tucker conditions generalize Lagrange multipliers. They include stationarity, primal feasibility, dual feasibility, and complementary slackness. Under convexity and regularity conditions, these conditions may be sufficient for global optimality. Without convexity, they are generally only necessary for local candidates. Dual variables measure sensitivity to constraints. The dual function provides lower bounds for minimization problems. A duality gap measures the difference between primal and dual objective values. Strong duality means that this gap is zero at the optimum. Convex problems often admit strong duality under suitable constraint qualifications. Non-convex problems may have a positive duality gap. Variational inequalities extend optimization. They seek a point in a feasible set such that a specified vector field has a non-negative inner product with every feasible direction. Equilibrium problems, traffic flow, contact mechanics, and game theory can be written in this form. A convex optimization problem can be expressed as a variational inequality using its gradient or subgradient. Monotone operators generalize increasing functions. An operator T is monotone when the inner product of T of x minus T of y with x minus y is non-negative. Maximal monotone operator theory supports nonlinear equations, optimization, and evolution problems. Proximal methods solve problems involving non-smooth functions. The proximal operator of a function balances closeness to a point with reduction of the function value. For the absolute value function, the proximal operator produces soft thresholding. This is why it appears in sparse optimization. Operator splitting methods divide a difficult problem into simpler parts. The alternating direction method of multipliers combines decomposition with dual variables. It is useful when variables or data are distributed across several components. The theory of generalized derivatives handles functions that are not classically differentiable. A convex function has a subdifferential. The subdifferential at a point is the set of all supporting slopes or supporting hyperplanes. At a differentiable point, it contains only the ordinary gradient. At a corner, it may contain an interval or a higher dimensional set. The absolute value function has subdifferential from -1 to 1 at 0. A point minimizes a convex function exactly when 0 belongs to its subdifferential. This extends the usual condition that the gradient equals 0. Other generalized derivatives include Clark derivatives and distributional derivatives. They serve different purposes. One must not treat all generalized derivatives as the same object. Each is defined for a particular class of problems and preserves particular rules. The calculus of distributions is especially important in partial differential equations. A locally integrable function defines a distribution by integration against smooth test functions with compact support. The derivative of a distribution is defined by transferring differentiation onto the test function with a sign change. Every distribution has derivatives of all orders. This permits weak derivatives of functions that are not classically differentiable. Sobolev spaces contain functions with weak derivatives in LP spaces. The space W1, P consists, roughly, of functions whose first weak derivatives belong to LP. Sobolev spaces are complete. They are natural spaces for weak solutions of differential equations. A weak solution satisfies an integrated form of the equation, rather than the pointwise equation. Weak formulations are not merely approximations. They are exact formulations in a broader function space. They often allow existence where no classical solution exists. Regularity theory asks when a weak solution is actually smoother. The answer depends on the equation, coefficients, domain, and data. Elliptic equations often improve regularity. Rough input may produce smoother interior solutions. Hyperbolic equations propagate singularities. Parabolic equations smooth spatial irregularities over positive time. These are broad tendencies, not universal statements without hypotheses. Partial differential equations are often classified as elliptic, parabolic, or hyperbolic. For second-order linear equations in two variables, the classification depends on the discriminant of the principal coefficients. Elliptic equations resemble the Laplace equation. They often describe equilibrium. Parabolic equations resemble the heat equation. They describe diffusion and irreversible smoothing. Hyperbolic equations resemble the wave equation. They describe propagation with finite characteristic speeds. Nonlinear equations may change type from point to point. Conservation laws have the form that a time derivative of density plus the divergence of flux equals 0. Integrating over a region and applying the divergence theorem gives a balance law. The rate of change inside equals the negative net outward flux. Solutions can develop shocks, even from smooth initial data. A shock is a moving discontinuity. Classical derivatives fail there. Weak solutions allow discontinuities, but weak solutions may not be unique. An entropy condition selects the physically relevant solution. This entropy is related to admissibility and irreversibility. It is not always identical to statistical entropy. Though the concepts are connected in some physical systems, the method of characteristics converts certain first-order partial differential equations into ordinary differential equations along curves. Along characteristic curves, the equation simplifies. For transport equations, information moves along these curves. Characteristics can intersect. When they do, smooth solutions may break down and shocks may form. For Hamilton-Jacobi equations, characteristics are linked to Hamiltonian mechanics. The Hamilton-Jacobi equation also appears in optimal control and dynamic programming. A value function describes the optimal future cost from each state. The Hamilton-Jacobi-Bellman equation characterizes this value function. It is generally nonlinear. Classical solutions may not exist. Viscosity solutions provide an appropriate weak notion. The name does not require physical viscosity. It comes from approximation by equations with small diffusion terms. Viscosity solution theory gives comparison principles and uniqueness for broad classes of nonlinear equations. Optimal control studies how to choose inputs over time to influence a dynamic system. A controlled system may satisfy x prime equals f of x and u. The control u is chosen to minimize a cost. Potryagin's maximum principle gives necessary conditions through an adjoint variable. In a Hamiltonian, dynamic programming gives the Hamilton-Jacobi-Bellman equation. These approaches are related but not identical. The maximum principle resembles constrained variational calculus. Dynamic programming uses the principle of optimality. An optimal policy has the property that, after any initial segment, the remaining decisions must be optimal for the resulting state. In stochastic control, random disturbances are included. The value function may satisfy a second-order, nonlinear, partial differential equation. This connects probability, optimization, and analysis. Control theory also studies controllability and observability. Controllability asks whether inputs can move the system between states. Observability asks whether internal states can be reconstructed from outputs. For linear systems, rank conditions provide tests. A continuous time linear system x prime equals ax plus bu is controllable if a matrix built from b, ab, a squared b, and further terms has full rank. Observability uses a related matrix built from the output matrix and powers of A. Duality links the two concepts. Feedback control chooses input based on the current or estimated state. Stability is often analyzed with Lyapunov functions. A Lyapunov function is a scalar function that behaves like an energy. It is positive near an equilibrium and decreases along trajectories. If it decreases strictly, the equilibrium may be asymptotically stable. Lyapunov's direct method can prove stability without solving the differential equation. For linear systems, quadratic Lyapunov functions lead to matrix equations and inequalities. The algebraic Riccati equation appears in optimal control and filtering. The linear quadratic regulator minimizes a quadratic cost for a linear system. Its optimal feedback is linear. The Kalman filter estimates the state of a linear system from noisy measurements under Gaussian assumptions. It alternates between prediction and correction. The prediction uses the dynamic model. The correction uses the discrepancy between predicted and observed outputs. Covariance matrices quantify uncertainty. The Kalman gain balances model uncertainty against measurement uncertainty. For linear Gaussian systems, the filter gives a conditional mean and is optimal in mean square error. Nonlinear extensions include the extended Kalman filter, unscented Kalman filter, and particle filters. They use different approximations. No single method is best for every nonlinear problem. Stochastic filtering in continuous time leads to equations such as the Kalman-Bucy filter and nonlinear filtering equations. These topics rely on conditional probability, stochastic calculus, and functional analysis. Another advanced area is ergodic theory. Ergodic theory studies long-term behavior of dynamical systems while preserving a measure. A measure preserving transformation keeps the measure of sets unchanged. An invariant set is mapped into itself in the measure theoretic sense. A system is ergodic when invariant sets have measure zero or full measure. Informally, an ergodic system cannot be decomposed into smaller invariant regions of positive measure. The Birkhoff ergodic theorem states that time averages converge almost everywhere. Under ergodicity, the limiting time average equals the space average. This gives a rigorous form of the idea that one sufficiently long trajectory can represent the statistical behavior of the whole system. The theorem requires precise assumptions. Not every physical system is ergodic. Even when a system is ergodic, the convergence rate may be slow. Mixing is stronger than ergodicity. It means that sets become asymptotically independent under repeated evolution. There are several forms of mixing. Strong mixing, weak mixing, and other variants differ in strength. Entropy in dynamical systems measures complexity of orbit structure. Kolmogorov-Sinai entropy quantifies average information production. Positive entropy is associated with chaotic behavior, though chaos has several non-equivalent definitions. Topological entropy measures orbit complexity without requiring a probability measure. Symbolic dynamics represents trajectories by sequences of symbols. A partition divides the state space. As the system evolves, one records which partition element contains the state. The resulting symbolic sequence can reveal hidden combinatorial structure. Shift maps on sequences are basic models. They connect dynamical systems with coding theory and information theory. Fractals arise in geometry and dynamics. A fractal may display structure at many scales. The term has no single definition covering all uses. One common feature is a non-integer dimension. The Hausdorff dimension extends the idea of dimension. A line segment has Hausdorff dimension 1. A square has dimension 2. The middle third's Cantor set has dimension equal to the logarithm of 2 divided by the logarithm of 3. The Cantor set is uncountable. It has measure 0. It is closed. It contains no interval. Every point is an accumulation point. It is also totally disconnected. These properties make it a standard example in analysis and topology. The construction begins with the interval from 0 to 1. Remove the open middle third, then remove the open middle third of each remaining interval. Continue indefinitely. Points that remain have ternary expansions using only 0 and 2, apart from the usual ambiguity of terminating expansions. Self-similar sets are often generated by iterated function systems. Each map is a contraction. The Hutchinson theorem gives a unique compact set, invariant, under the family of contractions. The Asirpi-Sixki triangle is formed by 3 scaled copies of itself. Its dimension is the logarithm of 3 divided by the logarithm of 2. Fractal geometry also studies random fractals, multifractals, and irregular natural forms. Brownian paths have fractal properties. Their graph has Hausdorff dimension greater than 1. Coastline models, turbulence, and financial time series may show scaling behavior, though real data rarely follow exact mathematical self-similarity across unlimited scales. Scaling and renormalization are important in physics and probability. A system may look similar after rescaling. Critical phenomena near phase transitions often show power laws. Correlation lengths become large. Microscopic details may become less important than symmetry and dimension. The renormalization group studies how models change under changes of scale. Fixed points correspond to scale invariant behavior. Universality means that different microscopic systems can share the same critical exponents. This is a profound example of abstraction. The correct large-scale description may depend on only a few structural features. Statistical mechanics connects microscopic states with macroscopic quantities. A microstate specifies detailed particle information. A macrostate specifies quantities such as temperature, pressure, and volume. Entropy measures the number or probability weight of compatible microstates. In the Boltzmann formulation, entropy is proportional to the logarithm of multiplicity. The proportionality constant is Boltzmann's constant. In the Gibbs formulation, entropy is a sum or integral involving probabilities. The canonical distribution assigns probability proportional to e raised to negative energy divided by thermal energy. The partition function normalizes these probabilities. It also contains thermodynamic information. Derivatives of its logarithm yield expected energy and other quantities. Free energy combines energy and entropy. Equilibrium minimizes an appropriate free energy potential under specified conditions. The law of large numbers helps explain stable macroscopic behavior. When an enormous number of particles contribute, relative fluctuations can become small, yet near critical points, fluctuations become large and correlations extend over long distances. Quantum mechanics uses complex Hilbert spaces. A physical state is represented by a ray in Hilbert space. Observables are represented by self-adjoint operators. Possible measurement values correspond to spectral values. For a discrete spectrum, eigenvalues give possible outcomes. The state determines probabilities through squared inner product magnitudes. Time evolution of an isolated system is unitary. It is governed by the Schrödinger equation. The equation is linear. The wave function conforms superpositions. Measurement and interpretation introduce conceptual questions beyond the mathematical formalism. Different interpretations agree on standard experimental predictions in ordinary settings, but describe the meaning of the state differently. The uncertainty principle arises from non-commuting operators. For position and momentum, their commutator is proportional to the imaginary unit times the reduced Planck constant. A general uncertainty inequality bounds the product of standard deviations, using the expected commutator. This is not simply a statement about imperfect instruments. It follows from the structure of quantum states and observables. Spectral theory gives the mathematics behind decomposition into measurement outcomes. For bounded self-adjoint operators, the spectral theorem expresses the operator as an integral over projection-valued measures. Unbounded operators require careful domain definitions. Position and momentum are unbounded. Their domains are proper dense subspaces of Hilbert space. Ignoring domains can lead to invalid algebra. Quantum field theory combines quantum mechanics with special relativity in fields. Its mathematical foundation is more difficult. Fields become operator-valued distributions. Renormalization handles divergent expressions by relating bare parameters to measurable quantities. Perturbation series may be asymptotic rather than convergent. Rigorous constructions exist for some lower-dimensional models. A complete non-perturbative construction of realistic four-dimensional interacting quantum field theories remains a major challenge. Gauge theory describes fields with local symmetries. Electromagnetism is associated with an abelian gauge group. The strong and weak interactions use non-abelian gauge groups. Connections describe how internal states vary across spacetime. Curvature represents field strength. Fiber bundles provide the geometric framework. A fiber bundle consists of a total space, a base space, a typical fiber, and local product structure. Globally, the bundle may be twisted. The Modius strip is a simple example of a non-trivial line bundle over a circle. Tangent bundles collect all tangent spaces of a manifold. Principal bundles carry group symmetries. Characteristic classes measure global twisting. They are cohomological invariants. Chern classes, Staffel-Whitney classes, and Pontryagin classes are important examples. Topology can therefore constrain physical fields. The Aronoff-Bohm effect shows that global gauge structure can affect quantum phases even where local field strength vanishes along the particle paths. Differential forms provide a concise language for integration on manifolds. A zero form is a function. A one form can be integrated along curves. A two form can be integrated over surfaces. An exterior derivative raises degree by 1. Applying the exterior derivative twice gives 0. This simple identity contains familiar vector calculus facts. The curl of a gradient is 0. The divergence of a curl is 0. Closed forms have exterior derivative 0. Exact forms are exterior derivatives of lower degree forms. Every exact form is closed. The converse holds locally under suitable conditions by the Poincaré lemma. Globally, closed forms need not be exact. The difference is measured by de-Rham cohomology. On a circle, a closed one form may fail to be globally exact. Its integral around the circle can detect the obstruction. Cohomology converts local differential data into global topological information. The generalized Stokes theorem states that the integral of the exterior derivative of a form over a manifold equals the integral of the form over the boundary. This includes the fundamental theorem of calculus, Green's theorem, Stokes' theorem, and the divergence theorem. The same structural law appears in different dimensions. Boundary and derivative are dual. The boundary of a boundary is 0. The exterior derivative squared is 0. These parallel identities are central to algebraic topology. Homological algebra studies such chains and maps abstractly. A chain complex is a sequence of objects and boundary maps whose consecutive composition is zero. Homology measures elements killed by one boundary map but not produced by the previous one. Exact sequences record when images equal kernels. A short exact sequence describes an object assembled from a sub-object and a quotient. Long exact sequences connect invariants across related spaces. Derived functors measure the failure of simpler functors to preserve exactness. Extet and Tor are standard examples. These subjects may sound distant from calculus, but the same patterns recur. Kernel and image appeared in linear algebra. Exactness refines their relationship. Cohomology appears in differential geometry, number theory, and algebraic geometry. Algebraic geometry studies solutions of polynomial equations using algebra and geometry together. An affine algebraic set is the common zero set of a collection of polynomials. The coordinate ring consists of polynomial functions restricted to that set. Geometry is translated into properties of ideals and rings. Hilbert's basis theorem states that polynomial rings over noetherian rings are noetherian. In practical terms, ideals in polynomial rings over a field are finitely generated. The Hilbert-Nullstellensatz connects ideals with geometric zero sets over algebraically closed fields. Prime ideals correspond to irreducible geometric pieces. Maximal ideals correspond to points in the classical affine setting over an algebraically closed field. Singular points are points where the geometric object fails to be smooth. The Jacobian matrix helps detect them. A curve defined by y squared equals x cubed has a cusp at the origin. A curve defined by y squared equals x squared times x plus 1 has a crossing or node depending on its exact form. Resolution of singularities seeks to replace a singular space with a smoother one while preserving much of its structure. Hironica proved resolution in characteristic zero. The positive characteristic case remains more difficult in full generality. Projective geometry adds points at infinity. Projective n-space consists of lines through the origin in an n+1 dimensional vector space. Coordinates are homogeneous. Multiplying all coordinates by a non-zero scalar represents the same point. Parallel affine lines can meet at a projective point at infinity. Polynomial equations are homogenized to define projective varieties. Projective spaces have compactness-like algebraic properties. Many intersection statements become cleaner there. Bézou's theorem states, roughly, that two projective plane curves of degrees m and n intersect in m times n points when multiplicities are counted and appropriate common components are excluded. Complex solutions and points at infinity must be included. Modern algebraic geometry uses schemes. A scheme allows geometric spaces to include nilpotent elements and arithmetic information. The spectrum of a ring is the set of its prime ideals equipped with a topology and a structure sheaf. This construction treats number rings and polynomial rings within one geometric language. A sheaf assigns local data to open sets and explains how local pieces agree and combine. Continuous functions form a sheaf. Differentiable functions form a sheaf. Solutions of local differential equations may form sheaves. Sheaf cohomology measures obstructions to gluing local data into global data. This local to global principle is another recurring theme. A property may hold in every small neighborhood, but fail globally. A differential form may be locally exact, but not globally exact. Local coordinate solutions may fail to combine into a global object. A bundle may look like a product locally, but be twisted globally. Cohomology records these failures in algebraic form. Number theory enters algebraic geometry through Diophantine equations. A Diophantine equation seeks integer or rational solutions to polynomial equations. The equation x squared plus y squared equals z squared has infinitely many integer solutions. Primitive Pythagorean triples can be parametrized. Fermat's last theorem states that x to the power n plus y to the power n plus y to the power n equals z to the power n has no positive integer solutions for n greater than 2. Andrew Wiles proved the theorem in the 1990s, building on work with Richard Taylor and many earlier mathematicians. The proof did not proceed by elementary manipulation of the equation. It used elliptic curves, modular forms, and Galois representations. An elliptic curve can be represented by a non-singular cubic equation together with a distinguished point. Its points form an abelian group. The group law has a geometric construction using lines intersecting the cubic. Elliptic curves appear in number theory, cryptography, and complex analysis. Over the rational numbers, Mortall's theorem states that the group of rational points is finitely generated. The structure is a finite torsion subgroup plus a free abelian part of finite rank. Determining the rank can be difficult. The Burchard-Swinnerton-Dyer conjecture relates the rank to the behavior of an L function at a particular point. It is one of the Millennium Prize problems. Modular forms are highly symmetric complex analytic functions. They transform in prescribed ways under fractional linear transformations. They have Fourier expansions. Their coefficients often encode arithmetic information. The modularity theorem connects elliptic curves over the rational numbers with modular forms. This connection was central to the proof of Fermat's last theorem. L functions generalize the Riemann zeta function. They are built from arithmetic data. They often have Euler products and functional equations. Major conjectures connect their zeros and special values with algebraic and geometric structures. The Langlands program proposes a wide network of correspondences between number theory, representation theory, and geometry. It is not one theorem. It is a broad framework containing many conjectures and proven cases. Representation theory studies ways to express abstract groups through linear transformations. A representation assigns a matrix or linear operator to each group element while preserving multiplication. This converts group structure into linear algebra. An irreducible representation has no proper invariant subspace. General representations may decompose into irreducible pieces under suitable conditions. For finite groups over the complex numbers, Moschke's theorem guarantees complete reducibility. Characters record traces of representation matrices. Character theory can classify representations and simplify calculations. Representations of Lie groups and Lie algebras are central to physics. A Lie group is both a smooth manifold and a group with smooth multiplication and inversion. Examples include rotation groups, general linear groups, and unitary groups. The tangent space at the identity carries a Lie algebra. The Lie bracket measures the first-order failure of group elements to commute. For matrix groups, the bracket is AB minus BA. The exponential map sends Lie algebra elements to Lie group elements. For matrix groups, it is the matrix exponential. Continuous symmetries are described by Lie groups. Infinitesimal symmetries are described by Lie algebras. The rotation group in 3 dimensions is non-commutative. Rotating around one axis and then another generally differs from reversing the order. The corresponding Lie algebra consists of skew-symmetric matrices. Quantum angular momentum uses representations of a related group in algebra. Symmetry classification in particle physics depends on representation theory. Root systems and Dynkin diagrams classify complex semi-simple Lie algebras. A small collection of diagram types describes infinite families and several exceptional cases. The exceptional Lie groups have names such as G2, F4, E6, E7, and E8. Their structures appear in geometry and theoretical physics. Representation theory also enters harmonic analysis. Fourier analysis on the circle decomposes functions into irreducible representations of the circle group. Fourier analysis on general groups replaces exponential functions with matrix coefficients of representations. The Peter-Weil theorem provides a decomposition for compact groups. Non-commutative harmonic analysis studies more complicated groups. Wavelets provide another form of function decomposition. Unlike global sine and cosine waves, wavelets are localized in both position and scale. A wavelet transform detects features at different resolutions. It is useful for compression, denoising, and signal analysis. Multi-resolution analysis organizes nested approximation spaces. The discrete wavelet transform can be implemented efficiently using filter banks. The Fourier transform gives precise frequency localization, but poor spatial localization. Wavelets balance the two. The uncertainty principle in harmonic analysis states that a function in its Fourier transform cannot both be arbitrarily concentrated. Several precise inequalities express this idea. The Gaussian achieves equality in the classical Heisenberg uncertainty inequality. Time-frequency analysis uses windows, short-time Fourier transforms, and wavelet transforms. Sampling theory asks when a continuous signal can be recovered from discrete measurements. The Shannon sampling theorem states that a band-limited signal can be reconstructed from samples taken faster than twice its highest frequency. The critical rate is associated with the Nyquist frequency. If sampling is too slow, aliasing occurs. Different frequencies become indistinguishable in the sampled data. Real signals are rarely perfectly band-limited. Practical systems use filters and safety margins. Signal reconstruction also depends on noise, quantization, and finite observation time. Inverse problems seek hidden causes from observed effects. Examples include medical imaging, astronomy, geophysics, and parameter estimation. A forward problem predicts observations from a model. An inverse problem attempts to recover the model or source. Inverse problems are often ill-posed. Solutions may not exist, may not be unique, or may be unstable. Regularization adds information or preference to stabilize recovery. Tikhonov regularization minimizes data mismatch plus a penalty on the solution. The penalty parameter balances fit and smoothness or size. Too little regularization amplifies noise. Too much regularization removes real structure. Choosing the parameter is itself a problem. Methods include cross-validation, discrepancy principles, and evidence-based approaches. Compressed sensing shows that some sparse signals can be recovered from fewer measurements than traditional dimension counting might suggest. The key assumptions are sparsity and suitable measurement structure. The recovery problem often minimizes an L1 norm subject to data constraints. Under restricted isometry or related conditions, exact or stable recovery is possible. This combines geometry, probability, optimization, and harmonic analysis. High-dimensional geometry differs from low-dimensional intuition. In a high-dimensional sphere, much of the volume lies near the boundary. Random vectors are often nearly orthogonal. Distances can concentrate around typical values. The concentration of measure principle states that many Lipschitz functions on high-dimensional spaces vary little around their median or mean. This phenomenon supports probability bounds, machine learning theory, and asymptotic geometry. The law of large numbers is one form of concentration. Chernoff, Hofding, Bernstein, and Azuma inequalities give exponential tail bounds under different assumptions. A sub-Gaussian random variable has tails no heavier than Gaussian tails up to constants. Sub-exponential variables have somewhat heavier but still controlled tails. Heavy-tailed variables may have finite means but large or infinite variances. Methods designed for Gaussian-like data can fail under heavy tails. Robust statistics seeks procedures less sensitive to outliers and model deviations. The median is more robust than the mean. Trimmed means discard extreme observations. M-estimators generalize maximum likelihood and least squares. Robust covariance estimation is more difficult in high dimensions. The breakdown point measures how much contamination an estimator can tolerate before becoming arbitrarily unreliable. The influence function measures sensitivity to a small amount of contamination. Statistical decision theory formalizes choices under uncertainty. A decision rule maps data to actions. A loss function assigns a cost to the action and true parameter. Risk is expected loss. A Bayes rule minimizes posterior expected loss under a prior. A minimax rule minimizes the worst-case risk. Admissibility means that no other rule has risk no greater everywhere and strictly smaller somewhere. Different principles may recommend different procedures. There is no universally best estimator without specifying the model and loss. Sufficient statistics compress data without losing information about a parameter under the model. The factorization theorem gives a criterion for sufficiency. A complete statistic can support unique, unbiased estimation. The Rao-Blackwell theorem improves an estimator by conditioning on a sufficient statistic. The Lehmann-Scheffé theorem identifies the unique minimum variance, unbiased estimator when a complete sufficient statistic exists. Fisher information measures sensitivity of the likelihood to a parameter. The Kramrow-Rao inequality gives a lower bound on the variance of unbiased estimators under regularity conditions. Maximum likelihood estimators often approach this bound asymptotically. The score is the derivative of the log likelihood. Its expected value is usually 0 under standard conditions. The variance of the score is the Fisher information. Information geometry treats probability distributions as points on a manifold. The Fisher information defines a Riemannian metric. Statistical models become curved geometric objects. Exponential families have a specially regular structure. A probability model belongs to an exponential family when its density can be written using a natural parameter, sufficient statistic, log partition function, and base measure. Normal, Bernoulli, Poisson, and many other standard distributions fit this form. The log partition function generates moments through derivatives. Convex duality connects natural parameters with mean parameters. Machine learning builds on optimization, probability, statistics, and computation. Supervised learning uses labeled examples. Unsupervised learning seeks structure without predefined labels. Reinforcement learning studies sequential decisions with rewards. A model is trained on finite data and evaluated on its ability to generalize. Generalization means performance on new data drawn from a relevant distribution. Empirical risk is average loss on the sample. Expected risk is average loss under the underlying distribution. Statistical learning theory studies when empirical risk approximates expected risk. Model complexity must be controlled. A model class that is too flexible can fit noise. A model class that is too restrictive can miss real patterns. The bias-variance trade-off describes one aspect of this balance. High bias comes from restrictive assumptions. High variance comes from strictive assumptions. High variance comes from sensitivity to sampling variation. Regularization, data volume, and model structure affect both. The Vapnik-Chervenenkis dimension measures the capacity of a class of binary classifiers. It is the largest number of points that can be labeled in every possible way by members of the class. Finite VC dimension supports uniform convergence bounds. These bounds connect sample size, complexity, confidence, and generalization error. Rademacher complexity provides a data-dependent measure of function class richness. Probably approximately correct learning formalizes learnability with accuracy and confidence parameters. No free lunch results state that, averaged over all possible data-generating rules, no learning algorithm is universally superior. Successful learning therefore depends on assumptions or inductive bias. Neural networks are compositions of affine maps and nonlinear activation functions. A feed-forward network passes information layer by layer. Training usually minimizes a loss by variance of gradient descent. Backpropagation computes gradients efficiently using the chain rule. The universal approximation theorem states that certain neural networks can approximate broad classes of continuous functions on compact sets when sufficiently wide. It does not say that training will find the approximation efficiently. It does not give a small network automatically. It does not guarantee generalization. Depth can represent some functions more efficiently than shallow width alone. Convolutional networks exploit local structure and translation-related patterns. Recurrent networks process sequences. Transformers use attention mechanisms. Attention computes weighted combinations based on similarities between queries and keys. Multiple heads allow several patterns of interaction. Positional information is required because pure self-attention does not inherently distinguish order. Large models contain many parameters that are trained on large datasets. Their behavior is shaped by architecture, optimization, data, scale, and post-training procedures. Mathematical understanding of their generalization and internal representation remains incomplete. Optimization landscapes are high-dimensional and non-convex. Yet over-parameterized systems can often be trained successfully. Classical intuition about unique, isolated minima does not fully describe this regime. Many parameter settings can represent similar functions. Symmetries create equivalent solutions. Stochastic gradient descent introduces noise through mini-batch sampling. This noise may influence which solutions are found. Curl methods offer another perspective. A kernel measures similarity and corresponds to an inner product in a possibly high-dimensional feature space. The kernel trick performs linear methods in that feature space without explicitly computing all coordinates. Support vector machines maximize a margin between classes. For linearly separable data, the hard margin classifier finds the separating hyperplane with largest minimum distance to the training points. Soft margins allow violations. Kernelized support vector machines produce nonlinear boundaries in the original input space. Gaussian processes place probability distributions over functions. A Gaussian process is specified by a mean function and covariance kernel. Any finite collection of function values has a multivariate normal distribution. Conditioning on observations gives a posterior process. The posterior mean provides a prediction. The posterior variance quantifies model-based uncertainty. Gaussian processes are flexible but can be computationally expensive for large datasets because standard methods require operations on dense covariance matrices. Approximation methods use inducing points, low-rank structures, or iterative solvers. Uncertainty quantification distinguishes different sources of uncertainty. Aleatoric uncertainty reflects inherent variability under the model. Epistemic uncertainty reflects limited knowledge or data. This distinction is useful but model-dependent. A model can misclassify uncertainty if its assumptions are wrong. Calibration asks whether predicted probabilities match observed frequencies. A model predicting probability 0.8 on many comparable cases should be correct about 80% of the time in a well-calibrated setting. Calibration does not guarantee accuracy or usefulness. A trivial model can be calibrated but uninformative. Proper scoring rules reward honest probabilistic predictions. The logarithmic score and Breyer score are examples. Causal inference asks what would happen under interventions. Association alone does not determine causation. A causal model distinguishes observing a variable from setting it to a value. Potential outcome notation compares outcomes under different treatments. Only one potential outcome is observed for each unit. This is the fundamental problem of causal inference. Randomized experiments use random assignment to balance confounding factors in expectation. Observational studies require assumptions and adjustment methods. A confounder influences both treatment and outcome. Conditioning on a collider can create spurious association. Causal diagrams represent variables and directed relationships. The backdoor criterion identifies sets that can block confounding paths under a graphical model. Instrumental variables can identify causal effects when a variable affects treatment, has no direct effect on the outcome, and satisfies independence assumptions. These assumptions are strong and often difficult to verify. Regression discontinuity uses a treatment threshold. Difference in differences compares changes over time between treated and comparison groups. Each method relies on assumptions. Parallel trends is central to basic difference in differences. Continuity near the threshold is central to regression discontinuity. No method removes the need for substantive knowledge. Game theory studies strategic interaction. A game specifies players, available actions, information, and payoffs. A strategy may be pure or mixed. A pure strategy selects one action. A mixed strategy assigns probabilities to actions. A Nash equilibrium is a strategy profile in which no player can improve by changing strategy alone. Every finite game has at least one mixed strategy. Nash equilibrium. The proof uses a fixed-point theorem. An equilibrium need not be unique. It need not be socially optimal. It need not be staple under every learning process. Dominant strategies are optimal regardless of other players' actions. They are stronger than Nash equilibrium strategies. The prisoner's dilemma has a dominant strategy equilibrium that is worse for both players than mutual cooperation. Repeated interaction can support cooperation under additional conditions. Backward induction solves finite perfect information games by reasoning from the end. Subgame perfect equilibrium requires strategies to form a Nash equilibrium in every subgame. This removes some non-credible threats. Games with incomplete information model private types. Bayesian Nash equilibrium specifies optimal strategies given beliefs about other players' types. Mechanism design reverses ordinary game theory. Instead of analyzing a fixed game, it designs rules to produce desired outcomes. The revelation principle states that under broad conditions, one can focus on mechanisms where participants truthfully report private information. Incentive compatibility means truthful participation is optimal. Individual rationality means participation is at least as good as the outside option. Auction theory studies allocation and payment rules. In a second price sealed bid auction with independent private values and standard assumptions, bidding one's true value is a dominant strategy. In a first price auction, optimal bids are generally below true values and depend on beliefs about competitors. Revenue equivalence states that several auction formats yield the same expected revenue under specific assumptions. Changing assumptions can break the equivalence. Cooperative game theory studies what groups can achieve together. The core contains allocations that no coalition can improve upon by leaving. The Shapley value assigns payoffs based on average marginal contributions across coalition orders. It satisfies axioms of efficiency, symmetry, null players, and additivity. Social choice theory studies collective decisions. Arrow's impossibility theorem states that no rank order voting system can satisfy a certain set of fairness conditions simultaneously when there are at least three alternatives and unrestricted preferences. The conditions include non-dictatorship, Pareto efficiency, and independence of irrelevant alternatives. The theorem does not say that collective decision-making is impossible. It shows that every method sacrifices at least one specified property. The Gibbard-Satterthwaite theorem states that every deterministic onto voting rule with at least three alternatives is manipulable unless it is dictatorial under standard conditions. Randomized rules and restricted preference domains create different possibilities. Third division studies allocation of goods or burdens. Proportionality, NV-freeness, efficiency, and strategy-proofness may conflict. For divisible goods, NV-free allocations exist under broad conditions. For indivisible goods, exact NV-freeness may be impossible. Approximate notions are then used. Mathematical economics uses fixed points, convexity, and optimization. General equilibrium theory studies prices and allocations across many markets. Under suitable assumptions, competitive equilibria exist. The welfare theorems connect competitive equilibria with Pareto efficiency. These theorems depend on assumptions such as complete markets, convex preferences, and absence of externalities. They are mathematical statements about models. They are not unconditional descriptions of every real economy. Finance uses probability and stochastic processes. The time value of money discounts future payments. A present value depends on interest rates and timing. An arbitrage is a strategy with no initial net cost, no possibility of loss, and positive gain in at least one scenario under a common simplified definition. The absence of arbitrage imposes pricing relations. In a one-period model, a contingent claim could be priced by replication if the market is complete. A risk-neutral probability measure is a transformed probability measure under which discounted asset prices are martingales. It is a pricing device. It does not necessarily represent actual beliefs about future outcomes. The fundamental theorem of asset pricing links absence of arbitrage with existence of an equivalent martingale measure. Market completeness corresponds to uniqueness of that measure under suitable finite-dimensional conditions. The Black-Scholes model assumes, among other conditions, continuous trading, constant volatility, and log-normal stock dynamics. It produces a partial differential equation for derivative prices. The price of a European option can be expressed using the standard normal distribution. The model is influential but idealized. Real markets show changing volatility, jumps, transaction costs, and liquidity constraints. Implied volatility is the volatility value that makes the model price match the market price. Across strike prices and maturities, implied volatility is not constant. Its surface contains information about market prices and model limitations. Risk management uses quantities such as value at risk and expected shortfall. Value at risk gives a loss threshold exceeded with a specified probability over a chosen horizon under a model. It does not describe the average loss beyond that threshold. Expected shortfall averages losses in the tail beyond a quantile. It has stronger coherence properties under standard definitions. Both depend on data, assumptions, horizon, and market conditions. Extreme value theory studies rare large observations. It provides limit laws for maxima and threshold exceedances. The generalized extreme value distribution describes normalized block maxima. The generalized Pareto distribution describes exceedances over high thresholds. Tail estimation is difficult because extreme events are rare by definition. Small samples produce large uncertainty. Dependence between extremes complicates the problem. Copulas separate marginal distributions from dependent structure. Sklar's theorem states that a joint distribution can be expressed using its marginals and a copula. For continuous marginals, the copula is unique. Linear correlation does not fully describe dependence. Different copulas can have the same correlation but different tail dependence. Modeling dependence requires more than choosing marginal distributions. Operations research applies mathematics to decisions and systems. Queuing theory studies waiting lines. A queuing model specifies arrival processes, service processes, numbers of servers, capacity, and service discipline. The notation m/m/1 describes Poisson arrivals, exponential service times, and one server. When the arrival rate is lower than the service rate, a stationary distribution exists. The traffic intensity is the arrival rate divided by the service rate. As traffic intensity approaches 1, expected waiting time grows sharply. Little's law states that the long-run average number in a stable system equals the arrival rate times the average time in the system. This relationship is remarkably general. It does not require exponential distributions. It requires suitable stability in averaging conditions. Inventory theory balances ordering costs, holding costs, and shortage risks. The economic order quantity model gives a square root formula under constant demand and several simplifying assumptions. More realistic models include uncertain demand, lead times, service levels, and multiple products. Dynamic programming solves sequential optimization by breaking problems into stages. A value function records the best achievable future result from each state. Bellman equations express recursive optimality. The curse of dimensionality refers to the rapid growth of state space. Approximation, decomposition, and simulation are used to manage it. Monte Carlo methods estimate quantities through random sampling. The error of an ordinary Monte Carlo average typically decreases proportionally to 1 divided by the square root of the number of samples. This rate does not directly depend on dimension, which is useful. But the variance may still be large. Variance reduction methods include control variates, antithetic variables, importance sampling, and stratification. Importance sampling changes the sampling distribution and corrects with weights. It is effective when the alternative distribution places more mass in important regions. Poorly chosen weights can produce extreme variance. Markov chain Monte Carlo constructs a Markov chain with a desired stationary distribution. After sufficient convergence, chain states approximate samples from the target. The Metropolis-Hastings algorithm proposes a move and accepts it with a probability correcting for target and proposal densities. Gibbs sampling updates components from conditional distributions. Hamiltonian Monte Carlo uses gradients and simulated mechanical trajectories to make efficient distant proposals. Diagnosing convergence is difficult. A chain can appear stable while exploring only part of the distribution. Multiple chains, effective sample size, autocorrelation, and domain-specific checks are used. No finite diagnostic can prove perfect convergence in every case. Quasi-Monte Carlo replaces random samples with low discrepancy sequences. It aims to fill the integration region more evenly. For sufficiently regular integrands, convergence can be faster than ordinary Monte Carlo. Randomized quasi-Monte Carlo adds randomness while preserving uniformity properties and allowing error estimation. Simulation also depends on random number generation. Computers usually generate pseudo-random numbers through deterministic algorithms. The seed determines the sequence. Good generators pass statistical tests and have long periods. Cryptographic generators require stronger unpredictability than ordinary simulation generators. A method suitable for Monte Carlo may be unsuitable for cryptographic keys. Computational geometry studies algorithms for geometric objects. The convex hull of a point set is the smallest convex set containing the points. In 2 dimensions, it is a polygon whose vertices are extreme points. Algorithms such as Graham scan and divide and conquer computed efficiently. Moranoy diagrams partition space according to nearest sites. Each cell contains points closest to one generating site. The dual structure is the Delaunay triangulation. Delaunay triangulations avoid thin triangles in a precise angle maximizing sense and are useful in meshing. Geometric algorithms must handle degeneracies. Points may be collinear. Distances may tie. Floating point errors may reverse orientation tests. Robust computation uses exact predicates, symbolic perturbation, or carefully designed arithmetic. A theoretically correct algorithm can fail in implementation if numerical signs are computed incorrectly. This returns us to the interaction between pure and applied mathematics. Dethmichon's guide theory. Algorithms translate theory into procedures. Numerical representation determines what a machine can actually perform. Data quality determines whether a model corresponds to reality. Interpretation determines whether the result answers the intended question. Each layer can introduce error. Mathematical maturity includes locating the layer where uncertainty enters. Some uncertainty is logical. The assumptions may not imply a unique answer. Some is numerical. Finite precision alters computation. Some is numerical. Finite precision alters computation. Some is statistical. The data are a random sample. Some is structural. The model omits relevant mechanisms. Some is computational. The exact solution is too expensive to obtain. Some is epistemic. Necessary parameters are unknown. A responsible conclusion states which form is present. Sensitivity analysis varies assumptions or inputs and observes the effect. Local sensitivity uses derivatives. Global sensitivity examines variation across a wider domain. Condition numbers measure worst-case local amplification. Scenario analysis compares selected alternatives. Probabilistic sensitivity assigns distributions to uncertain inputs. Robust optimization seeks solutions that perform acceptably across uncertainty sets. Stochastic optimization minimizes expected cost or another risk measure. Distributionally robust optimization considers a family of possible probability distributions. These approaches reflect different meanings of uncertainty. Robust optimization can be conservative. Stochastic optimization can be conservative. Stochastic optimization can be sensitive to distributional misspecification. Distributionally robust methods balance the two, but introduce their own modeling choices. Multi-objective optimization considers several objectives. No single solution may minimize all of them. A solution is Pareto optimal when no objective can be improved without worsening another. The Pareto frontier contains trade-off solutions. Choosing among them requires preferences or additional criteria. A weighted sum converts several objectives into one, but it may fail to recover every Pareto point in non-convex problems. Other methods use constraints, lexicographic priorities, or utility functions. Decision analysis includes expected utility. A utility function represents preferences over outcomes under axioms. Expected utility is calculated under probabilities. Risk aversion corresponds to concavity of utility in wealth. Jensen's inequality explains why the utility of expected wealth can exceed expected utility under concavity. Jensen's inequality states that for a convex function, the function of an expectation is no greater than the expectation of the function under suitable integrability. For concave functions, the inequality reverses. This theorem appears throughout probability, economics, information theory, and analysis. Convexity gives many inequalities. The arithmetic mean is at least the geometric mean for non-negative numbers. The Cauchy-Schwarz inequality compares inner products and norms. Alder's inequality generalizes it to conjugate exponents. Minkowski's inequality gives the triangle inequality in LP spaces. Young's inequality bounds products using powers. These results are not isolated tricks. They express the geometry of convexity and duality. Inequalities often provide estimates when exact calculation is impossible. Analysis depends heavily on bounds. One seeks upper and lower estimates. An asymptotic estimate describes behavior as a variable grows or approaches a point. Big O notation gives an upper order bound. The statement f of n is big O of g of n means that the absolute value of f is eventually bounded by a constant times the absolute value of g. Little o means the ratio approaches 0. Big omega gives a lower order bound in common computer science usage. Theta gives matching upper and lower orders. Different fields sometimes use notation differently. The exact definition should be stated. Asymptotic equivalence means the ratio of two quantities approaches 1. This is stronger than having the same big O order. The prime counting function is asymptotic to x divided by log x. Saying both are of the same order gives less information. Perturbation theory studies changes in solutions when a parameter is small. A regular perturbation expands the solution in a power series of the parameter. A singular perturbation occurs when the small parameter multiplies a highest derivative or changes the nature of the problem. The limit can lose order or boundary conditions. Boundary layers may form. In a boundary layer, the solution changes rapidly over a narrow region. Matched asymptotic expansions combine an inner solution near the layer with an outer solution away from it. Multiple scale analysis handles slow and fast variables simultaneously. These methods are common in fluid mechanics, oscillations, and wave theory. Asymptotic series may provide excellent approximations even when they diverge. A series is asymptotic when truncating after a suitable number of terms gives an error smaller than the last retained scale as the parameter approaches a limit. Adding too many terms can worsen the approximation. The optimal truncation point may depend on the parameter. Divergence, therefore, does not make an asymptotic series useless. It changes how the series must be interpreted. Special functions arise as solutions to important differential equations. The gamma function extends factorials. For positive integers n, gamma of n equals n minus 1 factorial. It is defined by an improper integral for positive real arguments and extended meromorphically. The beta function is related to products and ratios of gamma functions. Bessel functions solve equations with cylindrical symmetry. Legendre polynomials arise in spherical problems. Hermite polynomials appear in the quantum harmonic oscillator and Gaussian analysis. The Gare polynomials appear in radial quantum problems. Orthogonal polynomials form bases with respect to weighted inner products. They support approximation and numerical quadrature. Gaussian quadrature chooses nodes and weights so that polynomials of high degree are integrated exactly. With n suitable nodes, Gaussian quadrature can integrate polynomials up to degree 2n-1 exactly under standard conditions. The nodes are roots of orthogonal polynomials. This is a striking connection between approximation, linear algebra, and special functions. Approximation theory studies how well functions can be represented by simpler objects. Polynomial approximation is central. The Weierstrass approximation theorem states that every continuous real-valued function on a closed interval can be uniformly approximated by polynomials. It does not say that the Taylor series converges to the function. The approximating polynomials may be constructed by other means. Bernstein polynomials provide a constructive proof. Chebyshev polynomials are useful for near-optimal uniform approximation. They oscillate between extreme values in a controlled way. Chebyshev nodes reduce the Runge phenomenon in polynomial interpolation. The Runge phenomenon is large oscillation near interval endpoints when high-degree interpolation uses equally spaced nodes for certain functions. Interpolation matches data exactly at selected points. Approximation need not match exactly. Least squares approximation minimizes average squared error. Minimax approximation minimizes the maximum error. Spline functions use piecewise polynomials joined with smoothness conditions. Cubic splines are widely used because they balance flexibility and smoothness. Natural cubic splines impose zero-second derivative at endpoints. B-splines provide stable local basis functions. Changing one coefficient affects only a local region. This is valuable in design and computation. Approximation in high dimensions faces the curse of dimensionality. A grid with m points in each of d dimensions has m to the power d total points. The number grows exponentially with dimension. Sparse grids, low-rank tensor methods, random features, and structural assumptions attempt to reduce the burden. Dimension reduction seeks low-dimensional representations. Principal component analysis finds orthogonal directions of maximum variance. It is based on eigenvectors of the covariance matrix or singular vectors of the centered data matrix. The first component captures the largest possible variance among unit directions. Later components capture the largest remaining variance under orthogonality constraints. Principal component analysis is linear. It does not necessarily preserve nonlinear structure. It is sensitive to scaling and outliers. Manifold learning assumes data lie near a lower dimensional nonlinear manifold. Methods such as isomap, locally linear embedding, and diffusion maps use neighborhood relationships. Their success depends on sampling density, noise, distance choice, and manifold assumptions. Topological data analysis uses persistent homology. A scale parameter determines which data points or features are connected. As the scale changes, components, loops, and cavities appear and disappear. Persistence records the range of scales over which each feature exists. Long-lived features may represent structure. Short-lived features may represent noise, though this interpretation is not automatic. Persistence diagrams summarize birth and death scales. Stability theorems show that small changes in data produce controlled changes in these diagrams under suitable metrics. This gives a bridge between topology and data analysis. Geometry also enters probability through random geometry. A random geometric graph connects points that are sufficiently close. Percolation theory studies the formation of large connected clusters in random systems. In bond percolation, edges are randomly open or closed. In site percolation, vertices are randomly occupied or empty. A critical probability separates regimes with and without an infinite cluster on an infinite lattice. The exact critical value depends on the lattice and dimension. Near criticality, scale invariance, and fractal structure appear. First passage percolation assigns random travel times to edges and studies minimum time paths. Random matrix theory studies matrices with random entries. Their eigenvalue distributions often show universal behavior. For large symmetric random matrices with suitable independent entries, the empirical eigenvalue distribution may approach the semicircle law after scaling. Sample covariance matrices lead to the Marchenko-Pastor distribution. Largest eigenvalues can fluctuate according to Tracy-Woodham laws and several models. Random matrix theory appears in physics, statistics, number theory, and wireless communication. High-dimensional statistics must account for the case where the number of variables is comparable to or larger than the number of observations. Classical fixed-dimension asymptotics may fail. Sample covariance matrices become poorly conditioned. Spurious correlations can appear large. Regularization and sparsity assumptions become central. The lasso estimates sparse coefficients. Graphical lasso estimates sparse inverse covariance matrices. A zero entry in the inverse covariance corresponds to conditional independence for a multivariate normal distribution. Multiple testing arises when many hypotheses are examined. Testing each at a fixed significance level increases the chance of false positives. Family-wise error control limits the probability of at least one false rejection. The Bonferroni method divides the significance level by the number of tests. It is simple but can be conservative. False discovery rate control limits the expected proportion of false discoveries among rejected hypotheses. The Benjamini-Hochberg procedure is a standard method under certain dependence conditions. Selective inference accounts for the fact that hypotheses may be chosen after viewing data. Data reuse without adjustment can invalidate ordinary inferential guarantees. Reproducibility depends on transparent methods, suitable design, adequate power, and honest reporting. Mathematics can formalize error rates, but it cannot repair poorly defined questions or unreliable measurements by itself. Measurement theory studies how abstract quantities correspond to observations. A scale may be nominal, ordinal, interval, or ratio under a common classification. Nominal labels distinguish categories. Ordinal scales preserve order. Interval scales preserve differences up to linear transformations with positive slope. Ratio scales include a meaningful zero and preserve ratios under positive scaling. Permissible operations depend on the scale structure. In practice, real measurements may not fit these categories perfectly. Error models distinguish systematic and random errors. Systematic error shifts measurements in a consistent way. Random error varies unpredictably across observations. Repeated measurements can reduce random error in an average. They do not automatically remove systematic bias. Calibration compares an instrument with a reference. Traceability links measurements through a chain of standards. Uncertainty intervals should reflect known sources of variation and model limitations. Dimensional analysis checks physical units. A valid physical equation must be dimensionally consistent. The Buckingham pi theorem states that a physically meaningful relation among dimensional variables can be rewritten using a smaller number of dimensionless combinations under appropriate assumptions. Dimensionless numbers such as the Reynolds number, Mach number, and Froude number classify regimes. Similarity analysis allows laboratory models to represent larger systems when relevant dimensionless parameters match. The Reynolds number compares inertial and viscous effects in fluid flow. Low Reynolds numbers often correspond to smooth laminar behavior. High Reynolds numbers may support turbulence. The transition depends on geometry and disturbances. Turbulence remains a major mathematical and physical challenge. The Navier-Stokes equations describe viscous fluid motion. They express conservation of momentum together with incompressibility in a common model. In 3 dimensions, global existence and smoothness for arbitrary smoothed initial data remain unproved. This is another Millennium Prize problem. Weak solutions exist under broad conditions. Uniqueness and full regularity in 3 dimensions are unresolved. In 2 dimensions, the theory is better behaved. Turbulent flows transfer energy across scales. In 3-dimensional turbulence, energy often moves from large scales toward small scales where viscosity dissipates it. Kolmogorov's 1941 theory predicts scaling laws in an idealized inertial range. Intermittency creates deviations from simple scaling. Mathematical turbulence combines partial differential equations, probability, dynamical systems, and numerical simulation. Fluid equations also display vortices. Vorticity is the curl of velocity. In 2-dimensional incompressible ideal flow, vorticity is transported. In 3 dimensions, Vortex stretching can intensify vorticity. This term is one source of difficulty in the three-dimensional Navier-Stokes problem. Geophysical fluid dynamics adds rotation, stratification, and spherical geometry. The Coriolis effect influences large-scale atmospheric and oceanic motion. Potential vorticity combines rotation and stratification and is conserved under ideal conditions. Approximate balances, such as geostrophic balance, simplify large-scale models. Climate models couple fluid dynamics, radiation, chemistry, land processes, oceans, and ice. They are discretized numerical systems. Uncertainty arises from initial conditions, parameters, unresolved scales, and future forcing. Ensembles explore ranges of outcomes. Prediction at short weather timescales differs from projection under long-term scenarios. Both rely on models, but the sources and interpretation of uncertainty differ. Mathematics also studies networks beyond ordinary graphs. A network may have weighted, directed, temporal, or multi-layer edges. Centrality measures attempt to quantify importance. Degree centrality counts connections. Between a centrality counts shortest paths passing through a node. Eigenvector centrality rewards connections to other central nodes. PageRank modifies this idea using a random surfer model. Different centrality measures answer different questions. There is no single universal meaning of importance. Community detection seeks groups with dense internal connection. Modularity compares observed edge density with a null model. Maximizing modularity is computationally difficult and has a resolution limit. Stochastic block models generate graphs from latent groups. Inference estimates group membership and connection probabilities. Networks can exhibit small world structure. Average path lengths may be short even when clustering is high. Scale-free models produce heavy-tailed degree distributions. Preferential attachment is one mechanism. Real networks may show approximate heavy tails, but often deviate from pure power laws. Careful statistical testing is required. Epidemic models on networks differ from well-mixed models. Transmission depends on contact structure. The basic reproduction number summarizes expected secondary infections under specified conditions. Threshold behavior depends on network degree and correlations. Compartment models divide populations into states, such as susceptible, infected, and recovered. Differential equations describe average flows. Stochastic models describe random events. Spatial and network models add heterogeneity. Model parameters are context-dependent. A reproduction number is not a fixed property of a pathogen alone. It depends on behavior, immunity, environment, and interventions. Population dynamics includes interacting species. The Lotka-Volterra predator-prey model gives oscillatory solutions in an idealized form. The model assumes simple mass-action interactions and no resource limits for prey except predation. Real ecosystems require richer terms. Competition models describe species sharing resources. Mutualism models positive interaction. Reaction. Error in message stream. Retrie.